Hello there, and welcome to Physics with William, where curiosity gets comfortable and science takes its time. Tonight we're easing our way toward a very unusual question, one that sounds almost too extreme to be real. How hot can anything possibly get? Not how hot your tea becomes when you forget it for a moment, and then scorch your tongue in a burst of misplaced confidence. Not how hot a summer pavement feels under bare feet. Not even how hot a star burns as it pours light across the dark. I mean the upper edge of heat itself, the point beyond which our usual understanding begins to falter. The temperature so immense that physics, which is usually quite patient and well-behaved, starts to look a little shaken. Before we settle into that, I would love to know where in the world you're listening from tonight, and perhaps just for fun, whether you're wrapped in a blanket sitting beside an open window, or tucked into the sort of room that is always either a little too warm or a little too cold no matter what you do with the thermostat. It feels fitting somehow to begin a quiet discussion about the hottest temperature imaginable, while most of us are simply trying to get comfortable enough to drift off. If you find this soothing, or interesting, or just the right kind of strange to ease the day out of your mind, I would be very grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm find more people who enjoy ending the evening with something thoughtful and gentle. And if the topic happens to keep you awake for a while, well, there are worse reasons to lose a bit of sleep than wondering whether the universe itself once glowed at a temperature so fierce that our best theories still cannot fully describe it. Now, let's begin slowly, because this is one of those subjects that benefits from patience. The phrase Planck temperature has a certain intimidating quality to it. It sounds like the sort of thing one encounters in a textbook written by a person who has not seen daylight in several weeks. But hidden inside that rather formal name is a simple and deeply human question. Is there a final ceiling to heat? Can the universe become hotter and hotter forever without limit? Or does there come a point where asking for more heat stops making sense? Most of us grow up with a very ordinary relationship to temperature. We know what cold feels like when we step outside too early in the morning. We know the comfortable warmth of a shower, the dry heat of an oven, the warning sting of a pan that was clearly hotter than it looked. We talk about weather, fever, tea, soup, baths, blankets, summer pavement, winter radiators, and cars that somehow turn into greenhouses the moment the sun notices them. Temperature in daily life feels familiar. It is one of the first scientific ideas we meet without even calling it science. We feel it on our skin long before we ever hear the word thermodynamics. And because it feels so ordinary, it can be hard to remember just how strange temperature really is. You cannot hold it in your hand. You cannot pour it into a cup. You cannot point to a little glowing bead inside an object and say, there it is, that is the temperature. What you're actually noticing is motion. Tiny, restless motion. The ceaseless jostling and colliding of atoms and molecules. When something is warm, the particles inside it are moving around more energetically. When something is cold, they are calmer, though never perfectly still. Temperature is, in a sense, a measure of how frantically matter is dancing. Even that description, cozy as it may sound, hides a surprising amount of mystery. Because if heat is about motion, then it seems natural to assume that more heat simply means more motion, and more motion means still more heat, and so on without end. If a little energy makes particles move faster, then a lot of energy makes them move much faster, and an absurd amount of energy makes them move in ways that probably void several warranties. At first glance, nothing in that chain suggests an upper boundary. It feels like asking whether numbers can keep going. Surely you just add more. But nature has a habit of indulging our common sense only up to a point. It lets us feel comfortable just long enough to become a little smug, and then it quietly reveals that reality is under no obligation to be intuitive. The deeper physics goes, the more often this happens. You think time is the same for everyone until Einstein arrives and politely rearranges the universe. You think empty space is empty until quantum physics starts filling it with activity. You think heat is just more and more motion until you ask what happens when the energy becomes so enormous that the very structure of reality is pushed to its limits. That is where our story's going, though not all at once. For now, it helps to build a sense of scale. Human beings are not especially good at imagining extremes. We're very impressive in many respects. We write symphonies, launch telescopes, invent pasta shapes for reasons both practical and emotional. But our intuition evolved for medium-sized things: falling fruit, moving animals, campfires, rivers, weather, and the occasional rock that looks liftable until you attempt it and learn something about humility. We are not naturally equipped to feel the temperature at the core of a star, much less the conditions of the early universe. So when physics speaks of the hottest temperature possible, it is talking about a domain far beyond sensory experience. Consider the warmest things most of us encounter in ordinary life. A fresh cup of coffee, perhaps, a radiator, a summer day that seems determined to prove a point. Beyond that come ovens and furnaces and industrial flames, then lightning, which is far hotter than most people realise, then the surface of the sun, blazing at a temperature that already leaves everyday heat looking rather embarrassed. Move deeper into astrophysics and the scale rises rapidly. Stellar interiors, exploding stars, dense violent regions around collapsed objects, the early universe itself. Each step upward makes the last seem almost quaint. And yet, even the hottest star or the fiercest explosion is not what the phrase Planck temperature is really about. That term does not merely describe something astonishingly hot. It points toward a boundary where our separate theories of the universe begin to collide. On one side we have the physics of the very small quantum theory, which is exceptionally good at explaining particles, fields, radiation, and the jittery microscopic machinery of reality. On the other side we have the physics of the very large and very heavy general relativity, which describes gravity, space, time, and the architecture of the cosmos. Both theories are magnificent in their own domains. Both have passed test after test with remarkable success, and yet at sufficiently extreme conditions, such as those that may have existed in the earliest instant of the universe, both are needed at once. That is where the trouble begins. The Planck temperature sits in that neighbourhood. It marks a regime so extreme that the usual ways of describing matter and energy may no longer hold together. It is not simply a very large number that scientists enjoy mentioning to make everyone else feel underdressed. It is a signpost that says, beyond this point, the map becomes uncertain. There is something wonderfully humbling about that. Human beings have learned a tremendous amount about the universe. We know that stars are not holes in a dome, but spheres of plasma powered by processes deep in their cores. We know that atoms are mostly empty space, that light behaves both like a wave and like particles, that time is not as rigid as it seems, and that the night sky is crowded with galaxies far beyond anything our ancestors could have imagined. We can measure the age of rocks, detect planets around distant stars, and use clocks so precise that even a small change in height above the ground matters. And still there are thresholds where our understanding grows thin. This is one of them. The name Planck comes from Max Planck, the German physicist whose work helped begin quantum theory at the dawn of the 20th century. We will spend more time with him later, because he deserves better than a rushed introduction in the middle of a sleepy evening. For the moment, it is enough to know that Planck realised there are certain natural units that can be built from the fundamental constants of nature, units of length, time, mass and temperature that are not based on human habits, not on body parts or daily routines or the size of a metal ruler stored in a careful room somewhere, but on the fabric of physical law itself. The Planck temperature is one of those natural units. It is less a practical temperature than a conceptual frontier. Now at this point it is perfectly reasonable to wonder why any of this matters if nothing in our daily lives is ever going to approach such heat. After all, most of us are not in danger of accidentally setting our kitchen to early universe. We are not likely to peer into a saucepan and think, goodness, this soup appears to have entered a regime where quantum gravity becomes relevant. The kettle, even when forgotten, remains reassuringly local in its ambitions. But the value of an extreme limit is not that we expect to encounter it on the way to making toast. Its value is that it tells us something about the shape of the rules. The speed of light matters even if we are not commuting at relativistic speeds. Absolute zero matters even if our freezer is doing its best without quite reaching the foundations of thermodynamics. Limits reveal structure. They show us where a theory works, where it breaks, and where a deeper picture may be needed. And there is another reason this subject matters. The Planck temperature is not only about the far edge of heat, it is about the beginning. If our current cosmological picture is broadly correct, then the universe emerged from a state that was once vastly hotter and denser than anything we see now. As it expanded, it cooled. Structures formed. Particles settled into patterns. Light moved freely. Stars ignited. Galaxies assembled. Planets condensed. Chemistry became interesting. At least on one small world, living things eventually started asking questions about where it all came from. To understand the hottest temperature possible is to take a careful step toward understanding the earliest chapter of the cosmos, the point where the story becomes almost too compressed and bright to read. There is a subtle pleasure in that thought. Everything familiar around you, the bed you're in, the room you know in the dark, the soft hum of appliances, the distant traffic perhaps, the very atoms in your skin, all of it traces back through a chain of cooling and change. The iron in blood, the calcium in bone, the oxygen you breathe, the carbon arranged into the endlessly creative chemistry of life, all of it belongs to a universe that was once unimaginably hot. Not metaphorically hot, not just very warm indeed. Truly ferociously physically hot beyond ordinary language. Of course, language will try its best anyway, because that is what language does. It walks bravely toward the impossible carrying a small lantern. But the further we go into this topic, the more careful we have to become. Words like hot, particle, space, and even before begin to strain when pushed toward the earliest conditions of the universe. We keep using them because they are what we have, but each of them starts to bend. Take the word temperature itself. In everyday use it sounds simple enough. Yet even in physics, temperature is not just about raw energy floating around. It depends on systems being describable in a certain way. It depends on matter and radiation behaving statistically, on energy being distributed across states in ways that make the concept meaningful. At extreme enough conditions, the familiar distinctions between particles and forces can change. The ingredients may not even resemble the world we know. Asking for the temperature there is not impossible, but it comes with caveats. The closer we move to the Planck scale, the more our ordinary tools become approximations in a realm that may need an entirely new framework. That, oddly enough, is part of what makes the subject so calming to think about at night. Perhaps not calming in the sense of a warm cup of tea, though I would certainly recommend one. More calming in the sense that it loosens the grip of smaller worries. There is something clarifying about contemplating a scale so large and a temperature so immense that your unread emails are gently reduced to their proper significance. The mind, when faced with the foundations of reality, sometimes sets down its clutter for a while. Not always, of course. Sometimes it picks up new clutter. It starts wondering things like whether the universe had a beginning in time or merely in the form we can describe, whether space itself emerged from something deeper, whether gravity is fundamental or emergent, whether the laws of physics are inevitable or contingent, whether the early universe had one path or many possible histories. This is the sort of thinking that can either soothe you into sleep or keep you staring at the ceiling with the expression of someone who has just realized that existence is more complicated than the instruction manual suggested. Still, we will keep our footing. There is no need to race. Tonight we are not trying to solve all of fundamental physics before bedtime. We are simply opening the door and stepping into the hallway. We are getting used to the scale of the question. So let us return to the humble beginning. How hot can something get? At ordinary temperatures, matter is built from atoms and molecules moving in familiar ways. Raise the temperature enough and solids melt into liquids. Add more and liquids become gases. Increase it further and atoms lose their electrons and turn into plasma, that energetic soup found in stars and lightning. Already we have left the world of kitchen thermometers behind, but the climb continues. At higher energies, nuclei themselves can break apart. Under still more extreme conditions, protons and neutrons may no longer remain separate composite objects in the way we're used to thinking about them. The universe becomes less like a collection of neat pieces and more like a seething field of interactions, and yet even that does not quite reach the true frontier. The Planck temperature is not merely the point where matter is very agitated. It is the point where the concentration of energy is so profound that our current theories lose their confidence. Quantum effects of gravity, normally negligible, can no longer be ignored. Space and time, which in general relativity form a smooth stage on which events unfold, may cease to behave smoothly at all. The stage itself may become grainy, foamy, uncertain, or something stranger that our present language can only gesture toward. Imagine building a map of a coastline. From far away it looks smooth and clear. Move closer and you start noticing coves and ridges. Closer still and there are pebbles, grains, textures, variations. Eventually, the very idea of a smooth line becomes a convenience rather than a reality. Something similar may happen with space and time near the Planck scale. The large view works beautifully for stars, planets, and orbits. The microscopic view works beautifully for particles and fields. But at the deepest level, the concepts themselves may need revision. That is why the hottest possible temperature is not just a record to be broken. It is not the universe trying to win a contest against itself. It is a clue that our categories have limits. It tells us that if we want to understand the earliest instant of the cosmos, or the deepest structure of reality, we will likely need a theory that does not yet fully exist in finished form. Scientists have been trying to build such a theory for a long time. There are candidates, ideas, frameworks, mathematical proposals. Some suggest that the fundamental constituents of reality are not point particles but vibrating strings. Others suggest space is built from quantized structures. Some explore holographic descriptions, loops, networks, emergent geometries, or other ingenious attempts to reconcile the large and the small. Each offers insight. None has yet become the final agreed picture, which means that the Planck temperature stands not only as a limit, but as an invitation. That invitation is one of the reasons I find this topic so appealing. It reminds us that science is not a finished shelf of neat answers. It is a living effort. There are places where it speaks with extraordinary precision and places where it still lowers its voice and says here our knowledge becomes tentative. There is dignity in that, perhaps even comfort. The universe remains richer than our current explanations, and there is room in it still for discovery. As we continue, we're going to move from the familiar warmth of ordinary objects to the far more demanding idea of what temperature actually measures. We will climb through stars, plasma, and the young universe. We will meet Max Planck properly, and we will see why his name ended up attached to this astonishing boundary. We will also ask a very unsettling question. If the Planck temperature is the hottest temperature possible, in what sense is it possible at all? Is it something the universe truly reached, or is it a warning label attached to the edge of our current understanding? For now, though, let the mind rest in the strangeness of the basic idea. Somewhere in the language of physics there exists a temperature so high that beyond it our theories begin to blur. A temperature linked not to ovens or stars or even ordinary explosions, but to the possible birth conditions of reality itself. And before we can make sense of that frontier, it helps to slow down and ask the quieter question underneath it. When physicists speak of heat in the first place, what are they really measuring when they say that something is hot? There is a point where heat stops behaving like a familiar household nuisance and starts becoming something much stranger. Most of us know heat in its ordinary forms: the warmth of a mug between your hands, the radiating breath of an oven that has clearly been working harder than you have, the sudden punishment of a car seat left in the summer sun. These are the temperatures that shape daily life. They are serious enough to matter, mild enough to be manageable, and well within the range where the world still behaves like the world we know. Water boils when it should. Metal gets hot and then hotter. Bread becomes toast if watched carefully and becomes regret if not. Everything remains comfortably within the realm of common sense. But ordinary heat is only the shallow end of a very deep pool. Raise the temperature far enough, and the familiar world begins to peel apart layer by layer. The substances we rely on stop acting like themselves. Solids lose their structure. Liquids stop behaving like stable, cohesive things. Gases become so energetic that atoms can no longer hold on to their electrons. Matter starts shedding its usual identity, and the higher you go, the more dramatic this stripping away becomes. It is as though heat is not merely making things hotter, but asking them, with increasing firmness, what they are really made of. That is one of the reasons this subject is so captivating. We often think of temperature as a simple dial. A little more means warmer, much more means very warm indeed. But temperature is not just quantity, it is also transformation. At certain thresholds, adding heat does not merely intensify what is already there, it changes the rules of the game. The material enters a new state, the old language becomes insufficient. Something deeper has been exposed. You can see the beginning of this even in simple examples. Ice does not gradually become a slightly softer ice forever. At a certain point, its structure breaks down and it becomes liquid water. Keep going, and water itself stops being a liquid and becomes vapour. Those changes are so ordinary that we barely pause to admire them, but they are already hints that heat is not a passive background condition. It is an active force in the arrangement of matter. It decides whether molecules stay ordered or drift apart, whether structures endure or fall into motion. At human scales, that feels intuitive enough. Things melt, things boil, things burn. We may not phrase it in the language of molecular motion, but we understand the pattern. What becomes more interesting is that the pattern does not stop. There is no point where nature says you have now reached the final sensible state of matter, and everything beyond this is just more of the same. The universe remains inventive under pressure. Matter keeps changing character as the temperature climbs. Take a flame, for example. Fire seems ancient and simple, a companion of human life so old that it feels almost pre-scientific. We cook with it, gather around it, warn children about it, and stare into it with an attention that is either profound or merely hereditary. A flame is already a chemically busy environment, with molecules breaking apart, atoms colliding, light being emitted, and hot gases rising in chaotic patterns. Yet from the point of view of high-energy physics, an ordinary flame is not especially hot. It is barely the opening act. Fire is dramatic to us because we are soft, flammable creatures with strong opinions about remaining intact. The universe, by contrast, regards a candle with the sort of polite indifference one reserves for a very minor weather event. Even the surface of the sun, dazzling and severe by human standards, is still part of a larger ladder. It is hot enough to rip apart most ordinary materials with complete ease, yet the solar surface is not even the hottest region of the sun itself. Deeper within, the temperatures rise further, and in other cosmic settings they rise far further still. Stellar interiors, violent collisions, exploding stars, and the early universe all occupy regimes where ordinary language starts to feel quaint. You can still call it heat, but it is no longer the sort that warms your hands or bakes a potato. It becomes structural, primal, almost forensic. It reveals what matter is when all comfort has been removed. One useful way to think about increasing temperature is that it gives particles less and less patience for staying bound together. In a solid, atoms occupy relatively fixed positions, vibrating in place. They have enough energy to wiggle, but not enough to break free. In a liquid, they can move past one another, still close but less rigidly organised. In a gas, they roam much more freely. Those are the versions of matter that schoolrooms and kitchens teach us to expect. Solid, liquid, gas, neat, orderly, reassuring. Then things get less tidy. If you heat a gas enough, collisions become violent enough to strip electrons away from atoms. You're left with a soup of charged particles, electrons and ions, moving in a highly energetic state called plasma. Plasma is often described as the fourth state of matter, though by the time physics is done inventing states, one begins to suspect matter has a flair for reinvention. Plasma is common in the universe, even if it feels exotic on Earth. Stars are made of it. Lightning briefly creates it. Certain lamps and industrial processes rely on it. It conducts electricity, responds strongly to magnetic fields, and behaves differently from the ordinary gases that most of us think of when we imagine heated air. Already, by this point, heat has stopped being an ordinary property of stuff and started producing conditions where matter behaves collectively in unfamiliar ways. A plasma is not just a hotter gas in the casual sense. It is a state in which the previous identity of atoms has been undone. The electrons are no longer tucked neatly around nuclei in the way chemistry prefers. The everyday world of molecules and materials has given way to something rougher and more fundamental. Yet even plasma is not the end of the story. It only feels exotic because daily life rarely wanders into that territory, unless someone has badly mismanaged a power line. Keep climbing, and the very nuclei at the heart of atoms are no longer safe from the rising violence. Protons and neutrons, which seem so stable in the matter around us, are themselves built from smaller ingredients called quarks, held together by force-carrying particles called gluons. Under sufficiently extreme temperatures and densities, the usual locked arrangement inside protons and neutrons can give way. Instead of tidy little packages, quarks and gluons can move in a collective state known as a quark-gluon plasma. This is not a poetic exaggeration. It is an actual physical state, believed to have existed naturally in the early universe when everything was much hotter and denser than it is now. For a fleeting moment after the universe began its expansion, the conditions were so extreme that matter as we know it had not yet settled into atoms, or even into protons and neutrons in the stable forms we're used to. It was a much rawer environment, an energetic fluid of fundamental constituents not yet arranged into the familiar architecture of the modern cosmos. There is something almost unsettling about that idea. The chairs in our homes, the trees outside, the stones, the oceans, the body lying quietly beneath a blanket at the end of a long day, all of this depends on the universe having cooled enough for stable structures to emerge. If the temperature is too high, complexity cannot hold itself together. Matter is too agitated, too forceful, too unwilling to settle. The world becomes not a place of objects but of processes, not things but turbulence. Heat then can be thought of as a kind of undoing. It does not destroy indiscriminately in the childish sense of smashing things with a hammer. It peels back layers of structure. Molecules become atoms. Atoms become nuclei and electrons. Nuclei lose their integrity. Familiar particles reveal their own constituents. And at each level, what once seemed fundamental turns out to be provisional. Something deeper was waiting underneath. That progression gives us a more mature sense of what temperature means in extreme physics. It is not just a scale of discomfort or combustion. It is a measure of how deep into the structure of matter you are forcing the universe to look. A cool world is one where stable patterns can persist. A hot world is one where patterns break apart and hidden layers are exposed. An unimaginably hot world is one where even the language of particles may begin to strain. This is where the phrase, ordinary heat, becomes genuinely inadequate. At low temperatures, we can often ignore the microscopic details and still do quite well. You do not need a quantum theory of matter to know that soup left on the stove gets hotter. You do not need to solve the deep mysteries of the early universe to know that touching a hot tray is a bad idea. Everyday heat is forgiving in that way. It lets you function with intuition. It is the physics of baths and baking, radiators and weather forecasts. But once heat becomes extreme, intuition starts falling behind. We need theory, we need experiments, we need mathematics, we need particle accelerators, telescopes, detectors, and some very patient people who have accepted that their career involves studying things nobody can directly see and almost nobody can casually chat about at family gatherings. Because the world of extraordinary heat is not visible in the same way as ordinary warmth. It must be inferred, reconstructed, measured through traces and consequences. One of the remarkable achievements of modern physics is that we have in fact managed to study some of these extreme states. We cannot bottle the early universe, unfortunately, though one suspects the label would be difficult to print and the storage instructions rather demanding. But in high-energy particle collisions, scientists can briefly recreate tiny pockets of matter at enormous temperatures. These conditions last for only the briefest intervals, but they are enough to reveal how matter behaves when pushed beyond its ordinary forms. In those collisions, the familiar structure of protons and neutrons gives way, if only momentarily, to the kind of quark-gluon state that once filled the young cosmos. There is a quiet elegance in that. By smashing tiny particles together at extraordinary speeds, human beings on one small planet can catch glimpses of the physical conditions that existed when the universe itself was in its infancy. It is a lovely mixture of precision and audacity. We are, in effect, using elaborate machinery to ask existence what it was like when it had just arrived. Still, there are limits even to that ambition. The temperatures created in such experiments, vast though they are, remain far below the most extreme boundary we are heading toward. They are enough to melt the internal structure of matter, enough to access states unknown to ordinary experience, but not enough to reach the final frontier suggested by the Planck scale. That boundary remains in a different category altogether. To appreciate why, it helps to notice something about every extreme temperature we have discussed so far. However strange the resulting states become, we are still, broadly speaking, working within known frameworks. We can talk about particles, fields, interactions, and collective states using theories that have been spectacularly successful. The world may be violent and unfamiliar at those energies, but our equations are still on speaking terms with it. The Planck regime is different. There the concern is not merely that matter changes phase or that particles behave in unusual ways. The concern is that the very background structure within which all these things occur, space and time themselves, may no longer be describable by our current understanding. The heat becomes so extreme that gravity, usually negligible in particle physics, can no longer be treated as an afterthought. Quantum behaviour and gravitational behaviour must both matter at once. That is where our current two great frameworks begin stepping on each other's toes. This is one of the hardest ideas to absorb, perhaps because we are used to thinking of heat as something that happens to matter in space, not to space itself. We imagine a hot object sitting somewhere, glowing perhaps, while the stage on which it sits remains unaffected. But at truly extreme energies, the stage is no longer passive. Energy contributes to gravity. Gravity shapes space-time. At sufficient intensity, the conditions may be so severe that the distinction between what is heating and what is being heated starts to lose its ordinary meaning. That is why the journey upward through increasing temperature is not simply a list of hotter and hotter examples. It is a conceptual ladder. Each rung teaches us that the next level is not just more of the last, but a deeper challenge to the categories we began with. Solid becomes liquid. Liquid becomes gas. Gas becomes plasma. Plasma gives way to more fundamental states. And eventually the theories that describe all of those may themselves need replacing or extending. There is something almost archaeological about it. The hotter the system, the further back you dig into the underlying reality. Except instead of brushing dust from a buried statue, you are stripping structure from matter itself. The past you uncover is not human history, but cosmic history. The deeper layer is not an old city, but the early universe. And the early universe, as far as our best models indicate, was not a place in the ordinary sense. It was not full of stars and planets and drifting clouds. It was not waiting patiently for galaxies to decorate it. It was a condition, dense and rapidly changing, with energy levels beyond anything now common in nature. As it expanded, it cooled, and only then could the structures we know begin to emerge. In that sense, the history of the cosmos is also a history of heat becoming less extreme. The world became more familiar by becoming cooler. That is an oddly comforting thought. The stable world of evenings and rooms and quiet voices exists because the universe has been relaxing for a very long time. It has been stepping down from unimaginable intensity into the layered complexity that eventually allowed chemistry, planets, weather, memory and sleep. Every ordinary object is, in a sense, what remains after cosmic heat gave up enough of its grip for structure to survive. So when heat stops being ordinary, what we are really seeing is the reverse of that story. We are following the trail backward toward a state where the familiar world had not yet condensed into being. We are asking how far the peeling away can go. We are watching matter surrender its usual identities one by one. And in doing so, we arrive at a more precise question than the one we started with. Not just how hot can something get, but what does it even mean to call something hot when the usual forms of matter are gone? When particles stop behaving like tidy building blocks, and when the very framework of space and time may no longer be smooth enough for our familiar definitions to rest on. Before we can approach the upper limit itself, we need to pause over that quieter, more foundational point. Because once heat becomes extraordinary, temperature is no longer just a number on a scale, but a statement about motion, energy, and how the universe chooses to organize itself. When we use the word temperature in everyday life, we usually mean something very simple. We mean how hot or cold something feels. We mean whether the room is comfortable, whether the bath needs more hot water, whether the tea is safe to drink yet, or whether stepping outside in the morning was a mistake. Temperature in that sense feels immediate and personal. It belongs to skin and breath, and the small negotiations we conduct with weather, blankets, ovens, and windows. It is one of the first physical ideas we learn without needing anyone to define it for us. But that easy familiarity hides a deeper strangeness. Because the moment physics tries to answer what temperature really is, the idea becomes more subtle than it first appears. Temperature is not heat in the loose everyday sense. It is not simply warmth itself. It is not a substance stored inside objects like invisible soup. It is not a thing that sits in a mug or a stone or a patch of sunlight waiting to be released. What temperature really measures is something more basic and more abstract. It tells us about the energy of motion among the microscopic ingredients of a system. Not the motion of the whole object drifting across a table or falling from a shelf, but the restless internal motion of its particles. That may sound straightforward enough at first. Hotter things have particles moving around more energetically. Cooler things have particles moving around less energetically. And in broad terms, that is true. But as soon as you begin looking more carefully, even that neat summary starts developing qualifications, which is often how physics lets you know you are getting close to something interesting. Take a simple object, perhaps a cup of tea. When the tea is hot, the molecules inside it are in more vigorous motion. They jostle, rotate, vibrate, collide, and exchange energy constantly. When the tea cools, that microscopic agitation becomes less intense. The liquid still moves at the particle level, but with less average energy associated with that motion. Temperature, then, is linked to that average microscopic kinetic activity. In loose terms, the hotter the tea, the more frantically its molecules are moving. This picture is helpful because it replaces the old intuitive sense of hotness with something physical and measurable. Heat stops being a feeling and becomes a statistical statement about countless particles. That word statistical matters more than it may first seem. Temperature is not usually about the exact behaviour of one molecule or one atom. It is about huge collections of them. It is a collective description, a summary of the internal state of a system made up of many moving parts. One particle can have a particular energy. A whole swarm of particles can have a temperature. This is part of why temperature can sometimes feel slippery as a concept. It is not a property in quite the same way that mass or charge is a property. a single electron has a charge, a single atom has a mass. But when we speak of temperature in the usual thermodynamic sense, we're generally speaking about ensembles, large collections, systems whose microscopic chaos can be summarized by a few macroscopic quantities. Temperature belongs to the world of averages, distributions, and collective behavior. It is one of the great achievements of physics that something so chaotic at the small scale can become so orderly at the large scale. There is a certain quiet elegance to that. Imagine trying to track every molecule in a cup of tea. Every collision, every vibration, every tiny transfer of energy. It would be hopelessly complicated, yet instead of surrendering, physics takes a wiser route. It says we do not need to know every detail. We can talk about averages. We can talk about the overall distribution of energies. We can describe the whole system with a few broad quantities such as temperature, pressure, and volume. This is not because the details do not matter, but because when there are enough particles involved, patterns emerge. Temperature is one of those patterns. In that sense, temperature is a kind of summary language. It compresses vast microscopic complexity into a single usable number. It tells you something real, but it does so by ignoring nearly all the individual details. If you like, it is the universe allowing us to be practical. It is nature saying you may not know what every particle is doing. But here is a large-scale regularity you can rely on. That practical regularity has limits, though, and one of the best ways to understand temperature properly is to notice where our everyday intuition about it begins to fail. For example, people often assume that a hotter object always contains more heat than a cooler one. But that is not necessarily true. A tiny spark can be far hotter than a bathtub full of warm water, even though the bathtub contains much more total thermal energy overall. Temperature is not the same thing as total energy. It measures average energy per relevant degree of motion, not the total amount of energy in the entire system. This distinction matters because it reminds us that temperature is about intensity, not sheer quantity. A single glowing ember can have a very high temperature without containing much total thermal energy. A large lake can have a relatively low temperature while containing an immense amount of total energy, because there is so much water. The same confusion appears when people use the words heat and temperature as if they were interchangeable. They're closely related but not identical. Heat refers to energy in transit, moving from one system to another because of a temperature difference. Temperature refers to the condition that determines the direction of that exchange. That may sound a bit formal, but the idea is simple enough. If you place a hot spoon in cool soup, energy flows from the spoon into the soup. We call that transfer heat. The reason the transfer happens in that direction is that the spoon and the soup have different temperatures. Once they reach the same temperature, that particular net flow stops. So heat is not what an object contains in quite the ordinary sense. It is energy being exchanged because a difference exists. Temperature is the measure that tells us which way that exchange wants to go. This becomes clearer if you think about thermal equilibrium. When two systems are allowed to interact, they tend to exchange energy until they reach the same temperature. At that point, they are said to be in thermal equilibrium. No net heat flows from one to the other. That simple fact sits underneath thermometers, refrigerators, engines, weather, cooking, and much of ordinary life. It is so familiar that we rarely stop to marvel at it, but it is one of the most fundamental organizing principles in physics. Left to themselves, systems tend toward equilibrium. Temperature is one of the quantities that tells us what that equilibrium looks like. Now, all of this already gives us a much richer picture than the everyday feeling of hot and cold. But we still need to be careful, because when physicists say temperature measures average microscopic motion, the word motion can mean slightly different things depending on the system. In a gas, the picture is often close to what we imagine. Molecules move freely, flying about and colliding. So temperature is strongly connected to their translational kinetic energy, the energy of motion through space. In a solid, things are different. The atoms do not typically wander freely through the material. Instead, they vibrate around relatively fixed positions. Their thermal energy shows up more as collective vibrations than as free-roaming flight. In molecules, there can also be rotational motion and internal vibrational modes. In other words, temperature is not tied to just one simple kind of movement. It reflects how energy is distributed among the available microscopic degrees of freedom. That phrase may sound severe, but it points to something intuitive. Different systems have different ways of storing energy. A gas can store energy in flying around. A solid can store it in vibrations. A complex molecule can twist, bend, stretch, and rotate in many ways. Temperature helps describe how populated these different microscopic motions are on average. It is not one motion, but a whole internal economy of motion. And because it is an economy, not all forms of energy count equally toward temperature. This is another place where everyday intuition can mislead us. Suppose you're holding a bowling ball and walking quickly across a room. The bowling ball has kinetic energy because it is moving with you. But that bulk motion of the whole object does not mean the ball has a high temperature. You can have an object moving rapidly through space while being very cold internally. Temperature is not about how fast the whole thing is travelling relative to the room. It is about the internal microscopic agitation relative to its own centre of mass, if one wants to be precise about it. That difference turns out to be important in many areas of physics. An object can be moving rapidly through the universe and still have a low internal temperature. Likewise, a hot gas in a sealed container may have no overall motion at all relative to the room, while internally its particles are darting about chaotically. Temperature belongs to the inner disorderly dance, not the outer journey. The word disorder has now crept in, and that brings us toward another crucial aspect of temperature. Temperature is tied not only to energy, but to the number of ways energy can be arranged microscopically. This is where thermodynamics and statistical mechanics deepen the story. When energy enters a system, the question is not only how much energy there is, but how many different microscopic configurations are compatible with the large-scale state. Systems tend to move towards states that are more probable, meaning states that can be realized in more microscopic ways. Temperature becomes linked to how the entropy of a system changes as energy is added. That is not the sort of sentence most people want embroidered on a pillow, but it contains a profound truth. Temperature is not just about particles moving quickly. It is about the relationship between energy and the multiplicity of microscopic states. This is why thermal physics feels different from mechanics. Mechanics often tracks precise motion. Thermal physics accepts that precision is hopeless at the particle level, and instead studies probabilities, averages, and the overall tendency of systems to spread energy around. One might say that temperature is what emerges when too many tiny details become impossible to follow individually. It is not ignorance exactly, but organized ignorance. We know the laws governing the particles. We simply do not need to track each one. Instead, we describe the system in terms of average properties. That's a lovely piece of intellectual economy. It allows a universe of unimaginable, microscopic complexity to produce something as simple and useful as a temperature reading. There are moments, however, when even that large-scale simplicity becomes less straightforward. Consider very small systems. If you had only a handful of particles, the idea of temperature becomes awkward. Fluctuations matter too much. The smooth averaging that works so beautifully for a cup of tea or a room full of air no longer works as well. Likewise, in systems far from equilibrium, assigning a single temperature may not make sense. A system can have different parts with different effective temperatures, or different kinds of motion that have not yet settled into a common distribution. Temperature is most cleanly defined in conditions where equilibrium or near equilibrium exists. This is worth pausing over because it shows that temperature is not as universal and automatic as our thermometers suggest. We use the word freely because our daily world happens to live in conditions where the concept works beautifully. But the deeper truth is that temperature is a derived concept, a robust one, a powerful one, but still dependent on the system being of the right sort. It is not just pasted onto reality. It emerges from certain patterns in reality. That becomes especially important as we push toward extremes. At very low temperatures, quantum effects become increasingly significant. Systems can enter collective quantum states that have no counterpart in ordinary life. At very high temperatures, the available microscopic states change because matter itself changes form. The degrees of freedom that matter at one temperature may not be the same as those that matter at another. A solid, a plasma, and a quark-gluon plasma are not just hotter versions of the same stuff. They are physically different regimes with different relevant constituents and interactions. So when we ask what temperature really measures, the best answer is not a single sentence but a layered one. It measures how energy is distributed among the microscopic degrees of freedom of a system in or near thermal equilibrium. It reflects the average internal agitation, but also the statistical organization of states, the tendency of energy to spread itself through the available modes of motion. It tells us how eager a system is to give up energy to another system. It indicates where equilibrium lies. It belongs not just to motion, but to the whole probabilistic architecture of matter. There is also a subtle psychological reason why this topic matters. Human beings are quite comfortable with visible motion. We understand a rolling ball, a falling leaf, steam rising from a cup. What temperature does is force us to accept that the stillness we see is often an illusion of scale. A table looks still, but its atoms are vibrating. Air looks empty and calm, but its molecules are in ceaseless motion. Metal feels rigid and fixed, yet at the microscopic level it is alive with thermal agitation. Temperature reveals the hidden life inside apparently quiet things. That is perhaps one of the most satisfying shifts in perspective physics offers. It teaches us that calm surfaces can hide extraordinary activity. A quiet room at night is full of moving molecules. The wall beside you is not truly static. Your own body, resting under a blanket, is a coordinated thermal system of astonishing complexity, constantly regulating, exchanging, producing, and distributing energy. Life itself depends on maintaining gradients, flows, and balances that would collapse if temperature ceased to behave as it does. It also helps explain why temperature is so central to the history of the universe. The early cosmos was not merely bright. It was thermally structured in a way that determined what kinds of particles could exist, what interactions could occur, and when stable forms of matter could emerge. As the universe expanded and cooled, new possibilities opened. Certain particles stopped being created as readily. Bound states became stable. Light eventually travelled freely. The thermal history of the universe is not a side detail. It is one of the main scripts along which cosmic structure unfolded. And that brings us back to the larger path we are following. If temperature is this deep, this statistical, this dependent on the available microscopic states, then asking about the highest possible temperature is not as simple as asking how fast particles can move. It becomes a question about what the relevant constituents even are, what counts as a degree of freedom, whether equilibrium still makes sense, and whether space-time itself remains a smooth backdrop for thermal behaviour. The more carefully we understand temperature, the more clearly we see why the Planck temperature is not just a very big number. It is a warning that our ordinary thermal concepts may be nearing the edge of their usefulness. Before we get there, though, it helps to linger with scale, because once temperature is understood as a measure of internal microscopic energy distribution, rather than as mere felt warmth, the next natural step is to climb, not abruptly but gradually. From ovens to stars, from stars to the young universe, from familiar heat to the great ladder of fire that leads toward the earliest conditions we can meaningfully discuss. That climb is easier to appreciate if we stop thinking about heat as a single scale and start thinking of it as a ladder. Not a neat ladder with evenly spaced rungs, but a steep, uneven one where each step upward carries us into a different physical world. At the lower end are the temperatures that matter to daily life. Warm skin, hot tea, baking trays, engine parts, boilers, furnaces. Higher up come flames, lightning, molten rock, industrial plasmas. Beyond that, we leave ordinary experience almost completely and enter the temperatures of stars, then the interiors of stars, then the violent temperatures reached when stars die badly, then the temperatures created for tiny instants in particle accelerators. And beyond even those, not in a laboratory or a furnace or a star, but in the earliest history of the cosmos itself, lies the young universe, when it was hotter than anything that exists naturally now. The reason it helps to picture a ladder is that our intuition does not handle giant differences in scale very well. Once something is simply called very hot, the mind tends to lump it all together. A candle, a welding torch, the sun, an exploding star, the early universe. They all seem to belong to the general category of things one should not touch. That is true as far as personal safety goes, but it is not very useful as physics. The real story lies in the differences between these temperatures, because each step upward changes what matter is able to do, what structures can survive, and what kinds of physical descriptions make sense. Start with the temperatures closest to home. A warm room feels comfortable because it sits in a narrow band that human bodies tolerate well. Move upward to boiling water and cooking oil, and the hot metal inside an oven, and you have reached a regime that can burn skin and rearrange food. But matter itself is still very ordinary. Molecules remain molecules, atoms remain atoms. Chemical bonds form and break, which is dramatic enough for dinner and unfortunate enough for anyone who has ever forgotten a tray in the oven, but the deeper structure of matter stays intact. This is heat operating in the world of chemistry. A flame already takes us a step beyond that. In a flame, molecules collide, break apart, recombine, and emit light. The process is chemically busy and visibly energetic, but even here the temperatures are modest compared with the greater ranges of nature. A candle flame is not the edge of physical possibility. It is barely a polite introduction. Put another way, a candle is impressive only if your frame of reference is a dark room and a birthday cake. The universe has seen worse. Lightning is a sharper reminder that ordinary weather can already outrun household heat by a wide margin. A lightning bolt briefly creates a channel of ionized air so hot that the air expands explosively, which is why thunder follows. The temperature inside that channel can exceed the surface temperature of the sun. That fact always deserves a brief pause, if only because it makes storms seem even less interested in our comfort than they already appear. Yet even lightning, dramatic as it is still not operating in the truly extreme regimes of high-energy astrophysics. It is an intense local event, not a fundamental boundary. Then we arrive at stars, which are the first really important rung on this ladder, because they force us to stop thinking of heat as accidental and start thinking of it as structural. A star is not merely a hot object glowing in the sky. It is a gravitationally confined sphere of plasma, whose entire existence depends on conditions deep in its interior. The surface of a star may be hot enough to reduce most earthly materials to problems, but the surface is not where the main story happens. The real heat is inside, where pressure and temperature rise enough for nuclear processes to occur. Our own sun is a good example, because it is so familiar and so easy to underestimate. To the eye it looks calm, even gentle at sunset, as though it has kindly agreed to end the day on a warm orange note. In reality, the sun is a nuclear engine. Its visible surface is already extremely hot, but the core is vastly hotter still. There the matter is compressed and energized enough for hydrogen nuclei to overcome their mutual resistance and fuse into heavier nuclei through a series of processes that release energy. That energy makes its long, difficult journey outward, bouncing, scattering, and convecting until it finally leaves as the light and heat that reach Earth. The sun, though, is a middleweight by cosmic standards. It is stable and long-lived, which is excellent news for us, and only mildly disappointing if one was hoping for a more theatrical neighbourhood. More massive stars are hotter in their cores. They burn through fuel more rapidly and more violently. Their internal temperatures climb high enough to support fusion stages beyond what occurs in the sun. They can build heavier and heavier nuclei in layered shells, rather like cosmic onions with deeply alarming interiors. Each new stage requires higher temperatures and pressures. In these stars, heat is not just a byproduct. It is what allows the next nuclear step to happen at all. This is an important point because it shows that higher temperatures are not simply more of the same. They unlock new processes. At one temperature, hydrogen can fuse under the right conditions. At higher temperatures, helium can fuse. Higher still, more advanced reactions become possible. The ladder is not just hotter, it is chemically and structurally transformative. Eventually, however, there comes a limit to what fusion can do for a massive star. A star can spend much of its life using heat from nuclear reactions to resist the inward pull of gravity. But once it builds up a core of the wrong kind, the balance fails. The result is one of the most violent events in the universe, the supernova. During such a collapse and explosion, temperatures rise to astonishing levels. Matter is compressed, shocked, and flooded with energy. Elements heavier than iron can be forged in these catastrophic environments. The blast throws enriched material into space, where later generations of stars and planets may form from it. This means that the calcium in bone, the iron in blood, and many of the heavy elements embedded in the world around us owe their existence to temperatures and pressures far beyond anything the calm, mature universe usually provides. A comfortable room may not feel especially connected to a stellar catastrophe, but the periodic table would disagree. The ordinary world is built from extraordinary thermal history. If stars and supernova take us partway up the ladder, there are other cosmic environments that force the temperature higher still. Matter falling onto dense objects such as neutron stars or black holes can be heated to extreme degrees in accretion disks, where gravitational energy is converted into heat and radiation with enormous efficiency. Gas spiraling inward becomes compressed and accelerated. Collisions and friction like processes within the disk raise its temperature until it glows in high-energy light. These are places where gravity and heat work together with little concern for simplicity. Even so, it helps to keep perspective. Astrophysical temperatures that sound extreme to us are still many rungs below the final boundary we're heading toward. They are terrifying, yes. Impressive, certainly. Fatal, immediately. But still not the hottest conditions physics allows us to contemplate. To continue the climb, we need to move from naturally occurring stars and stellar deaths to the highly controlled violence of modern particle accelerators. This may seem like a strange transition. One moment we're discussing stars the size of worlds. The next we're in underground facilities accelerating subatomic particles around enormous rings. But the connection is direct. If heat measures the distribution of energy among microscopic degrees of freedom, then the highest laboratory temperatures are produced not by making large things warm, but by packing enormous energy into tiny collisions. In those collisions, for the briefest moments, the energy density becomes so great that matter enters states not otherwise available on Earth. When heavy ions are collided at extremely high energies, they can produce a quark-gluon plasma. This is the state in which quarks and gluons are no longer confined inside individual protons and neutrons in the familiar way. Instead, for a fleeting instant, the system behaves like a strongly interacting fluid of these more fundamental constituents. It is not a gas of neat particles bouncing independently. It is a collective state, hot, dense, and deeply revealing. The temperatures reached in such collisions are immense, far beyond the core of the Sun and far beyond most ordinary astrophysical contexts. Yet they exist only in minuscule regions for vanishingly short times. That is enough. Physics does not always need duration. Sometimes a fraction of a second is sufficient to expose how nature behaves when pushed hard enough. These experiments are among our best windows into the kind of matter that filled the universe when it was very young, and that is where the ladder takes a decisive turn. Up to now, we have moved through present-day objects and events: kitchens, storms, stars, supernovae, accretion flows, particle collisions. Each of these exists within the universe as it is now, old, expanded, structured, and comparatively cool. But the highest natural temperatures were not reached in rare corners of the modern universe. They belonged to the universe itself in its earlier stages, when everything was compressed into a much denser and hotter state. The phrase early universe can sometimes sound abstract, as though it refers to a vague, distant concept rather than a real, physical history. But it is better to think of it as the thermal childhood of everything around us. The universe expanded from a denser earlier state, and as it expanded, it cooled. That cooling determined what could exist at each stage. At very high temperatures, particles could be created and destroyed readily. Certain distinctions among forces may not yet have existed in the forms familiar today. Stable atoms certainly did not exist. Even stable nuclei had to wait. The early universe was not a place full of objects. It was a rapidly evolving thermal system in which the basic ingredients of reality interacted under conditions we can only partly reproduce. One of the most important habits in cosmology is resisting the temptation to imagine the early universe as a hot explosion happening at some point in pre-existing empty space. That mental picture is persistent and misleading. The hot, dense early universe was not matter expanding into a waiting void like smoke from a firework. Space itself was part of the evolving system. The expansion happened everywhere, not outward from a single ordinary centre. So when we speak of the universe being hotter in the past, we mean the whole observable cosmos was once in a state of far greater energy density and temperature than it is now. As we look backward in time through our models, the temperature rises. Galaxies had not yet formed, then atoms had not yet formed, then nuclei had not yet formed. Earlier still, even protons and neutrons were not stable as separate bound structures in the way they are later. The universe passes through a sequence of thermal regimes, each one setting the stage for the next. It is a cooling story, a long gradual settling from enormous thermal intensity into the complexity we know. This is one of the reasons temperature is so central to cosmology. It is not just one property among many. It is one of the main coordinates of the universe's history. To say when something happened in the early universe is often almost the same as saying at what temperature it happened. The thermal state determines what particles exist abundantly, what reactions proceed efficiently, what symmetries are broken, and what structures can emerge. The universe cools, and in cooling, it becomes articulate. It develops durable matter, radiation backgrounds, chemistry, stars, planets, and eventually observers who ask unreasonably large questions late at night. Still, if we keep tracing the ladder upward, following the universe back to earlier and earlier times, the temperatures become more and more extreme. At some point, our tested theories remain informative, but increasingly strained. The particle physics we trust still guides much of the way. General relativity still tells us about cosmic expansion. Yet the closer we move toward the earliest instance, the more those two great frameworks begin to demand equal authority. Quantum effects matter. Gravity matters. Energy densities are enormous. And this is where the ladder no longer looks like a smooth extension of known physics, but starts to approach a frontier. That frontier is what makes the next step so important. There is a temperature scale associated with the natural constants of the universe, a scale at which the separation between quantum theory and gravity can no longer be maintained in the ordinary way. This is the realm named after Max Planck. The Planck temperature is not simply another rung above quark-gluon plasma and early cosmic fire, as though we were merely adding one more item to a list. It marks a regime where the rules used to describe the lower rungs may no longer be enough. That difference matters. A supernova is hotter than a stellar core in a meaningful but still familiar way. The early universe was hotter than a supernova in a meaningful way that particle physics can partly describe. But the Planck regime is different because it points not just to hotter matter, but to the possible breakdown of our present categories. Space and time themselves may no longer behave as smooth classical structures. The very concept of temperature may need more careful handling there because the microscopic degrees of freedom of space-time could become relevant. Before we go there, though, it is worth pausing on the scale we have already crossed, from boiling water to a flame, from lightning to the sun, from stellar cores to supernovae, from accretion disks to collider plasmas, from those brief laboratory recreations to the actual thermal history of the newborn cosmos. This is not merely a list of impressive numbers, it is a progression through deeper layers of physical reality. Each step upward strips away a piece of the ordinary world. Chemistry gives way to plasma physics. Plasma physics gives way to nuclear and particle physics. Particle physics eventually leads us toward cosmology and the structure of space-time itself. Seen that way, the ladder of fire is really a ladder of explanation. It tells us where different theories become necessary and where familiar matter loses its familiar identity. It reminds us that the world of daily life is not the whole of physical possibility. It is a late-cooled settle outcome. Stable, yes. Beautiful, certainly. But thermally modest compared with the conditions from which it emerged. And there is something quietly satisfying in recognizing that the universe has been cooling into complexity for a very long time. The reason there are atoms is that it cooled. The reason there are stars instead of only a uniform glare is that it cooled and structure could grow. The reason there are planets, oceans, chemistry and biology is that the cosmic furnace stepped down through countless thresholds and allowed matter to become selective, organized, and durable. The calm room you're in is one tiny local chapter in that much longer thermal descent. So when we speak of the hottest temperatures in nature, we are really speaking about the earliest and least settled stages of reality. We are following the history of heat backward toward a region where our current understanding becomes less secure. That is the point at which one particular name starts to matter more than all the stars and explosions we have just passed. Because once we have climbed from ordinary fire to cosmic fire, the next question is not just how much hotter things were, but whether nature itself has a built-in scale that tells us where our current map begins to fail. That is where Max Planck enters the story, and why his name became attached to so many of the deepest limits in physics. Before we can understand why the hottest possible temperature carries Planck's name, it helps to spend a little time with the man himself, because the story is more interesting than the label suggests. Max Planck does not enter the history of physics as a flamboyant rebel or a scientific showman. He was not the sort of figure who seems to arrive with a storm behind him. He was measured, disciplined, serious, and in many ways deeply conservative in his scientific instincts. He admired order. He respected continuity. He preferred clarity to drama. If you had asked him early in his career whether he intended to help overturn the foundations of classical physics, he likely would have found the idea faintly exhausting. And yet that is more or less what happened. There is something fitting about that. Science often changes not only through bold personalities announcing revolutions, but through careful people trying to fix a stubborn problem and accidentally discovering that the old framework cannot survive intact. Planck was one of those figures. He did not set out to make the universe stranger. He set out to understand a technical issue in the physics of heat and radiation. In doing so, he ended up opening the door to quantum theory, one of the deepest transformations in the history of science. To appreciate why that matters for our story, we need to place him in his moment. By the late 19th century, physics looked impressive and mature. Classical mechanics had given a coherent description of motion and forces. Thermodynamics had revealed broad laws governing heat, work, and energy. Electromagnetism had unified electricity, magnetism, and light in a powerful theoretical structure. There were puzzles, yes, but to many physicists the great framework of nature seemed almost complete. The broad outlines of reality appeared to be in place. This is usually the moment when reality prepares a correction. One of the problems that refused to behave involved blackbody radiation. The phrase sounds dramatic, but the underlying idea is fairly simple. Imagine an ideal object that absorbs all incoming radiation and, when heated, emits radiation in a characteristic way determined only by its temperature. Such an object is called a blackbody, not because it must look black in ordinary conditions, but because in the idealized sense it absorbs perfectly. The important thing is that the pattern of radiation emitted by such a body could be measured, and those measurements did not agree with the theoretical expectations produced by classical physics. At first glance, this sounds like a specialized technical headache, the sort of issue that would cause headaches in laboratories and put everyone else gently to sleep. But blackbody radiation turned out to be one of those cracks that reveal the deeper instability of an entire building. Classical theory predicted the wrong distribution of emitted energy. In particular, it implied that hotter objects should pour more and more energy into shorter and shorter wavelengths, in a way that led to absurdity. The mathematics pushed toward an unphysical catastrophe. Nature, as observed, declined to cooperate. Planck approached this problem with great seriousness and not a great deal of revolutionary ambition. He was trying to derive the correct radiation law. He wanted a formula that matched the data. In pursuing that goal, he made a move that at first may have seemed like a formal trick, almost a mathematical device rather than a declaration about reality. He proposed that the oscillators exchanging energy with radiation could not take on just any arbitrary amount of energy. Instead, the energy came in discrete packets, proportional to frequency. That was the key step. It is difficult to overstate how strange this was in context. Classical physics was built on continuity. Energy was supposed to vary smoothly, not arrive in little indivisible chunks. Planck's proposal broke with that expectation. At first, he did not fully frame it as a grand philosophical revolution. He was trying to save the theory from failure. But the idea worked. It matched the observed radiation law, and in doing so it introduced a new constant into physics, a constant that became one of the cornerstones of quantum theory. This is the first reason Planck's name appears so often near the deepest boundaries of nature. He did not merely solve a narrow radiation problem. He uncovered a sign that the microscopic world was organized in a way classical continuity could not describe. Energy exchange at the smallest scales had structure, discreteness, granularity, and once that door opened, the whole landscape of physics changed. The quantum world entered, first cautiously, then decisively. There is a quiet irony here that makes Planck especially appealing as a historical figure. He was not a man intoxicated by disorder. He was not eagerly trying to smash established ideas. In temperament, he leaned toward harmony and principle. Yet his work helped begin a period of physics in which harmony had to be rethought, and principle had to survive in stranger forms. It is one of the recurring lessons of science that nature does not reward loyalty to familiar pictures. It rewards accuracy, patience, and the willingness to follow evidence even when it leads into conceptual fog. Planck's contribution did not end with the quantum insight. The constant introduced through his radiation work soon became central to a more general realization. If the fundamental constants of nature tell us something about the architecture of reality, then perhaps one can build natural units from them, units that do not depend on human convenience. Most of the units we use in daily life have a local practical history. Seconds come from historical ways of dividing the day. Meters emerge from human attempts to standardize length. Degrees on temperature scales reflect conventions and calibration choices. Useful, certainly. Universal, not really. Planck recognized that from certain fundamental constants, one could define units of length, time, mass and temperature that belong to nature itself rather than to human custom. This was a profound shift in perspective. A natural unit does not care whether a civilization counts on fingers, uses pendulums, measures with rods, or argues endlessly about standards committees. It arises from the structure of physical law. In that sense, Planck units are not merely convenient conversions. They are signposts pointing towards scales where the basic ingredients of our theories meet one another. That idea deserves a slow explanation because it lies at the centre of why the Planck temperature matters. Different areas of physics introduce different constants that reveal different aspects of reality. One constant is tied to the quantum nature of action. Another is tied to the speed at which signals and causal influences propagate in relativity. Another governs the strength of gravity. If you combine these ingredients in the right conceptual way, you obtain characteristic scales where neither quantum theory, nor relativity, nor gravity can be treated as secondary. Those scales mark a domain in which all of them matter together. That is the real meaning of natural limits in this context. They are not necessarily walls in the childish sense, as though nature had built a fence and hung a sign that says "do not climb higher." They are scales at which our existing ways of dividing physical problems into separate categories stop working well. At ordinary scales, you can often ignore quantum effects and gravity. At laboratory quantum scales, you can often ignore gravity altogether. In the middle-sized world of daily life, both can safely recede into the background while classical approximations do most of the work. But the Planck scale is what happens when that comfortable separation collapses. Planck himself could not yet see the full future significance of these scales in the way later physics would. No one at the dawn of quantum theory had the completed map. Einstein had not yet developed general relativity. Quantum mechanics as a mature framework still lay ahead. Particle physics, cosmology, quantum field theory, black hole thermodynamics, early universe models and all the rest had not yet arrived in their modern forms. But the seeds were there. By isolating natural units, Planck had identified something like the joints of physical law, places where the constants that define our theories combine into scales that are not arbitrary. There is a kind of intellectual cleanliness in that. Human beings are fond of units that suit our bodies and our habits. A foot, a yard, an hour, a degree on one scale or another. Useful things, but parochial. Planck units ask a different question. Suppose you wanted a civilization anywhere in the universe, with no shared culture, no shared language, no shared measuring sticks, to identify a common scale based only on the laws of nature. What units would you choose then? The answer would not come from kings, calendars, or metal bars kept in protected rooms. It would come from the basic constants that appear in the physical description of the world. That is why Planck's name has an unusual prestige in physics. It is attached not merely to one discovery, but to a level of thinking about nature that seeks what is universal beneath convention. When physicists speak of the Planck length, the Planck time, the Planck mass, or the Planck temperature, they are not just honouring a historical figure, they are pointing to a set of scales where our ordinary conceptual partitions start to fail. This is particularly important for our question, because a limit like the Planck temperature is not just about heat, it is about the boundary between kinds of explanation. Below that regime, we can talk meaningfully about particles, radiation, thermal distributions, and even the early universe using theories that, while sometimes stretched, remain recognizable. But as we push toward the Planck scale, the assumptions underneath those theories begin to tremble. Space-time may no longer be smooth in the sense general relativity assumes. Quantum fluctuations of geometry itself may become unavoidable. Gravity may need a quantum description that no fully established theory has yet completed. That is what natural limits really mean here. They are not always hard prohibitions. Sometimes they are places where the language we have been using becomes insufficient. Consider how different physics would look if one knew only fluids and weather, and then suddenly tried to understand atoms. The old concepts might still be useful in their domain, but they would not be enough. Something analogous happens at the Planck scale. The familiar concepts from quantum theory and relativity may both still be partially right, but not complete on their own. Planck's life also lends an additional human texture to this story, because he lived through a period of tremendous intellectual and political upheaval. He was not insulated from hardship. The world around him changed violently. The Germany through which he lived was not the same place at the beginning and end of his life. He endured personal losses of a severe and painful kind. He watched science transform itself beyond the comfortable structures of the 19th century. Through all of this, he remained a figure of discipline, seriousness, and devotion to inquiry. There is something almost austere about him in the historical record, not cold exactly, but composed. That composure can make it easy to overlook how radical his scientific legacy became. Once the quantum idea had entered physics, the consequences multiplied. Einstein used the quantum idea in his explanation of the photoelectric effect. Bohr used quantum concepts in early atomic theory. Eventually, full quantum mechanics arrived with all its strangeness. The smooth classical world gave way to one in which discreteness, uncertainty, superposition, and quantized states became central. Planck had not built that whole edifice himself, but he had struck the first decisive blow against the assumption that classical continuity was enough. And because of that, his name now sits beside some of the deepest unresolved questions in modern physics. How do we reconcile gravity and quantum theory? What is the structure of space-time at the smallest scales? What were the true conditions at the beginning of the universe? What does it mean to speak of length, time, or temperature when the background geometry itself may fluctuate? These questions all gather near the Planck domain. There is a temptation, when discussing this, to treat the Planck scale as mystical. It is not mystical, it is physical. The difficulty lies not in some supernatural quality, but in the fact that the scales involved are so remote from ordinary experience and so demanding for theory that our tested frameworks no longer extend cleanly. Physics remains physics there, but it is physics not yet fully unified in our understanding. That distinction matters because the natural limits of nature are often misunderstood as dramatic stop signs. In reality, they're usually more informative and more subtle. The speed of light is not simply a number painted on the edge of reality to annoy ambitious drivers. It tells us something deep about space-time and causality. Absolute zero is not merely a lower end point of thermometers. It reflects the structure of thermal motion and the third law of thermodynamics. In a similar way, the Planck temperature is not just an extravagant upper number designed to impress the unwary. It tells us that beyond a certain regime, the concepts of temperature and energy density are entangled with the deepest unresolved architecture of space-time itself. Planck's natural units therefore serve as a bridge between known law and unknown theory. They mark where familiar descriptions give way to frontier questions. That is why meeting Planck in this story is not just a historical courtesy, it is necessary. Without him, the very language in which we discuss ultimate scales would look different. He provided one of the conceptual tools by which modern physics can even frame the question of an upper thermal limit in a meaningful, universal way. There is also something quietly comforting in the fact that this came from a careful mind trying to understand a stubborn discrepancy. Science at its best is often less glamorous than people imagine. It is not always a lone genius announcing truth from a mountain. Sometimes it is patient work on a problem that refuses to fit, a refusal to ignore mismatch, a willingness to follow a technical detail until it opens into a new world. Planck's path reflects that beautifully. He did not begin with the ambition to reinvent reality. He began with radiation data. The universe did the rest. So when we say Planck temperature, we're saying more than the name of a man. We're invoking the idea that the laws of nature themselves define characteristic scales. We are invoking the quantum hint that continuity fails in crucial places. We're invoking the confrontation between gravity and microscopic physics. And we are invoking a boundary region where our current maps become incomplete. The next step, then, is to stop speaking about that region in general terms and face the temperature itself. What does this hottest number in physics actually represent? How large is it in conceptual terms, not merely as a recited figure? Why do physicists treat it as a meaningful upper scale? And in what sense does it describe a real physical condition, rather than only a warning about the breakdown of present theory? Because once Planck's name has led us to the doorstep of natural limits, the obvious question is what exactly waits there when the universe becomes hot enough that even our best descriptions begin to lose their footing. Now we can finally look directly at the number that has been waiting behind all the earlier steps. The Planck temperature is often described as the hottest possible temperature, and that description is broadly useful, but only if we handle it carefully. It is not simply the largest number anyone managed to squeeze onto a physics chart after too much coffee and a very ambitious afternoon. It is not a record in the same way that the highest mountain or the fastest sprint might be called a record. It is more interesting than that, and also a little more troublesome. The Planck temperature marks a regime where our present theories of nature are no longer comfortable being treated separately. It is the scale at which quantum physics, gravity, energy and space-time all insist on being part of the same conversation. That alone makes it special. Most of physics works by dividing problems into manageable domains. If you're studying atoms, you usually do not need to worry about the gravitational influence of each electron. If you're studying planetary orbits, you usually do not need a quantum description of space-time. The world is kind enough, much of the time, to let us focus on the pieces that matter most and treat the rest as negligible. This is one of the reasons science can progress at all. The universe is complicated, but not always maximally complicated all at once. The Planck temperature is what happens when that kindness runs out. At lower temperatures, even very high ones, we can still use the tools of particle physics and thermodynamics to say meaningful things. We can describe how matter behaves as atoms break apart, as nuclei dissolve into more fundamental ingredients, as radiation fills the system, as particles are created and annihilated. We can model plasmas. We can discuss early universe conditions. We can recreate tiny fragments of those conditions in particle accelerators. Our theories, though pushed hard, remain recognizable. The mathematics may become demanding, but the framework is still one we trust. At the Planck temperature, by contrast, the challenge is not merely that matter becomes unfamiliar. The challenge is that space-time itself may no longer behave as the smooth stage our current theories often assume. Gravity becomes too important to ignore, but it must matter in a quantum regime where our best available description of gravity, general relativity, was never built to be quantum in the way that particle physics is. That is why the Planck temperature matters. It does not just say this is very hot. It says beyond this scale, the map you have been using is no longer enough. To get a feel for this, it helps to remember how we normally talk about temperature. Temperature is a summary of how energy is distributed among the microscopic degrees of freedom of a system. It works beautifully when there is a system to describe in those terms. A gas, a plasma, a field of radiation, a thermal bath of particles. But the closer one gets to the Planck regime, the more uncertain it becomes what the relevant microscopic degrees of freedom even are. Are we still talking about particles moving in a smooth space-time background? Are we talking about quantum fields defined on a geometry that can be treated classically? Or does geometry itself become part of the fluctuating quantum system in such an essential way that the ordinary meaning of thermal description begins to shift? That is why calling the Planck temperature the hottest possible temperature is both true and incomplete. It is true in the sense that it marks the upper scale at which our familiar thermal concepts can be extended with any confidence. It is incomplete because beyond that point the problem is not simply that nature forbids a larger number in a mechanical way. The deeper issue is that the very framework within which temperature is defined may need revision. The ceiling is therefore not just about heat, it is about comprehension. Still, it helps to be concrete. The Planck temperature is staggeringly beyond any temperature achieved in ordinary nature today. It is beyond stellar cores, beyond supernova interiors, beyond the hottest environments around compact objects, beyond the fleeting temperatures produced in the most powerful particle collisions humans have managed to create. If you tried to build a ladder of heat from a kitchen stove to the sun, and then onward through the hottest known astrophysical processes, you would still be nowhere near this final scale. The Planck temperature is not a slightly more dramatic extension of known fire. It is a different category altogether. That difference is worth sitting with. because large numbers often lose their emotional force when they become too abstract. The mind hears unimaginably hot and nods politely, but without much genuine understanding. We are not built to feel the difference between merely immense and truly ultimate, yet in physics the distinction matters. Many temperatures that seem absurdly large to human intuition are still, from the point of view of the deepest laws, comfortably below the regime where gravity must be quantized. The Planck temperature is where that comfort ends. It is also worth noticing that this temperature is not attached to some particular object. There is no Planck star glowing somewhere in a remote galaxy at exactly this level, as though nature had thoughtfully provided a demonstration model for the textbooks. The Planck temperature is a theoretical scale built from the fundamental constants of nature. It arises from combining the quantum constant associated with the graininess of action, the constant associated with the strength of gravity, the speed that structures relativistic causality, and the relation between energy and temperature. That combination produces a natural thermal scale. The point of doing this is not just to obtain an impressive number. The point is to identify where the known pillars of physics stop being separable. That gives the Planck temperature a somewhat unusual character. It is not only an estimate of an extreme physical condition, it is also a diagnosis. It tells us that if a system reached energies corresponding to that thermal scale, then any complete description would have to include a proper theory of quantum gravity. Since we do not yet possess such a fully confirmed and complete theory, the Planck temperature becomes both a landmark and a warning sign. This double role is what makes it so fascinating. On the one hand, it seems to point toward the earliest history of the universe, perhaps to a regime near the very beginning of cosmic expansion, where temperatures may have approached this scale. On the other hand, it reminds us that our confidence in describing such a regime is limited. We can extrapolate backward, we can infer, we can model the cooling history of the early cosmos with considerable success for eras after the most extreme beginning. But once we push all the way toward Planck-level conditions, the extrapolation enters territory where our present theories are not yet unified enough to be fully trusted. There is a strange dignity in that limit. Science is often at its best not when it pretends to know everything, but when it can say exactly where its certainty thins out. The Planck temperature is one of those boundaries. It is not ignorance in the broad, vague sense. It is sharply located ignorance. It tells us precisely which combination of ideas becomes problematic and why. That is a far more powerful kind of not yet than simple confusion. One way to think about the Planck temperature is as the thermal counterpart of other Planck scales. The Planck length suggests a size below which the smooth geometry of spacetime may cease to make classical sense. The Planck time suggests an interval so brief that speaking of earlier and later, using our present concepts may become questionable. The Planck mass points to a scale where quantum and gravitational effects meet in a particularly intimate way. The Planck temperature belongs to this family. It indicates the heat scale where energy density and microscopic structure become so extreme that the very arena in which thermal processes occur may no longer remain classical. That last point cannot be overstated. In almost all ordinary physics, space-time sits quietly in the background. It can be flat enough to ignore curvature, or gently curved in ways that general relativity handles beautifully, but it remains a stage. At the Planck temperature, the stage may become part of the performance in a fundamentally quantum sense. Distances may fluctuate. Geometric structure may no longer be describable as a smooth manifold in the way we usually assume. If that is right, then asking about temperature there is a bit like asking about the wind speed inside a dream, while the concept of air is still being invented. The question is not meaningless, but it belongs to a regime where the supporting concepts are themselves under construction. This is why physicists sometimes speak about the Planck temperature with a kind of respectful caution. It is not that they doubt the scale has significance. They doubt their ability to describe reality beyond it with current tools. That is an important difference. The Planck temperature is not arbitrary. It is deeply meaningful. but it is meaningful precisely because it marks the edge of what present theory can treat straightforwardly. There is another subtlety here as well. When people hear the phrase hottest possible temperature, they often imagine a fixed absolute barrier in the same intuitive style as a maximum setting on an oven. Turn the dial any further and nothing happens because the machine has reached its limit. Nature is rarely so domestically cooperative. The Planck temperature is not a dial stop in that literal sense. It is better understood as the scale at which the assumptions behind the dial itself become unreliable. Can one imagine mathematical models with energy densities associated with larger nominal temperatures? Certainly in a crude extrapolating sense. But whether the concept of temperature remains meaningful in the same way, and whether such a regime can be physically described without a deeper theory, is precisely the problem. That makes the Planck temperature less like the top rung of a simple ladder, and more like the edge of a map where the cartographer has written, "Beyond here the terrain changes and our old symbols fail." You can point toward it, you can estimate its location, you can say why it matters, but you cannot walk much further with confidence using the same guidebook. There is something quite beautiful in that. Much of modern physics is a story of pushing familiar concepts until they reveal their limits. Time seemed absolute until relativity bent it. Particles seemed like tiny billiard balls until quantum mechanics softened them into something far stranger. Empty space seemed empty until field theory filled it with structure and fluctuation. The Planck temperature continues that pattern. It tells us that even heat, one of the oldest and most familiar physical ideas, has a frontier where its standard description becomes entangled with the deepest unfinished business in science. And yet this frontier is not purely abstract. It matters because the universe itself may once have inhabited conditions close to it. If we trace cosmic history backward, the universe becomes denser and hotter. For a great deal of that backward journey, our theories do remarkably well. We can describe nuclear synthesis, the formation of light elements. We can describe the era when matter and radiation decoupled enough for light to travel freely. We can reconstruct much of the thermal evolution of the early cosmos with considerable confidence. But the closer we push toward the beginning, the hotter the universe becomes, and the more the Planck scale begins to loom. At around that regime, our current theories cease to provide a complete account. So in one sense, the Planck temperature is the hottest number in physics, because it names the ultimate thermal threshold of known theory. In another sense, it is the hottest number, because it stands nearest to the earliest inferable moments of cosmic history. It is the edge of the story we can tell before the script begins to dissolve into missing pages. There is an understandable temptation to ask whether anything could ever reach this temperature again. Could some future civilization build a machine that accesses that regime? Could black holes, collisions, or exotic phenomena recreate it? These are natural questions, and some of them will matter later. For now, it is enough to notice that even our most violent known processes fall astonishingly short in accessible practice. The Planck temperature is not a realistic engineering target in any ordinary sense. It belongs to a depth of reality that is less about technological ambition than about theoretical necessity. And still, despite all this caution, the phrase hottest possible temperature remains useful because it compresses the essential message. There is a point at which adding energy no longer fits comfortably inside the known compartments of physics. The world becomes too hot for us to keep gravity classical while keeping matter quantum. That is the heart of it. The temperature is less a boast than a summons. It tells us that a unified understanding is required, that unified understanding does not yet exist in fully confirmed final form. There are candidate approaches, ideas that attempt to quantize gravity or derive space-time from deeper structures. Some imagine fundamental strings, some imagine quantized loops or networks, some pursue holographic descriptions, some investigate emergent geometry. Each is an attempt to answer the challenge announced by the Planck scale. None has yet reached the status of settled law. The Planck temperature therefore functions like a question posed in the language of a number. It asks what is the true microscopic structure of space-time when heat and gravity become inseparable. There is also a more philosophical reward in thinking about this number. It reminds us that the universe is not built only from the scales we evolved to notice. Human senses are provincial. They're good enough for berries, weather, faces, and fire, but they are not tuned for quantum geometry. Science extends those senses by building concepts that can reach beyond direct intuition. The Planck temperature is one of the results of that extension. No one feels it, no one sees it directly. Yet by following the logic of physical law, we can identify it as a meaningful frontier. This, I think, is part of what makes the subject so satisfying to contemplate at night. It is difficult enough to quiet the mind without giving it better things to think about. The Planck temperature offers one such thing. It places ordinary concerns against a scale where even our best theories begin to hesitate. It reminds us that the world we know is a cool, settled arrangement resting on a much wilder foundation. And it suggests that the most intense heat imaginable is not merely destructive, but revelatory. It exposes the point where matter, radiation, gravity, and geometry can no longer be separated by habit. If the number itself is a frontier, then the natural next question is what exactly happens as one approaches it. What becomes of particles, of light, of space, when the temperature rises so high that our ordinary categories begin to blur? Because once the hottest number in physics has been placed on the horizon, the real intrigue lies in the landscape around it, where familiar distinctions weaken and the universe begins to look less like a collection of things and more like a single, violent, unresolved question. By the time we approach the highest thermal scales that physics can even discuss with a straight face, the universe stops looking like a place made of tidy ingredients. The familiar picture begins to loosen. Matter is no longer made of stable atoms. Atoms are no longer made of calmly sheltered nuclei with obedient electrons. Even protons and neutrons have already surrendered their usual identity. The world becomes more restless, more provisional, and far less willing to sort itself into the neat categories that work so well in ordinary life. The closer we move toward the Planck regime, the more it seems that the distinctions we rely on, matter and radiation, particle and field, object and background, begin to blur at the edges. This is not because physics becomes vague in the lazy sense, but because the structures we are trying to describe are being pushed into a domain where their usual definitions no longer stay clean. In everyday conditions, we can point to a particle and imagine it as a somewhat localized thing with certain properties. We can point to light and treat it as radiation, different in kind from matter, even if quantum theory later tells us the difference is subtler than it first appeared. We can point to space as the quiet stage on which both of those perform. That picture is already more approximate than common sense suspects, but it works beautifully across much of known physics. Then the temperature rises, the energy density climbs, the timescales shrink, and the world starts refusing to stay in separate boxes. One of the first hints of this appears long before the Planck scale itself. At sufficiently high energies, light can produce matter. Matter can annihilate into light. The boundary between the two, which feels so absolute in ordinary life, begins to look more like a reversible exchange. In a quiet room, a chair is matter and a lamp is light, and no one feels confused about the difference. In the deep furnace of high-energy physics, the distinction remains real, but it is no longer static. Energy can reorganize itself from one form into another. A radiation-filled environment can teem with particle creation and annihilation. What matters is not the old common-sense separation between substance and illumination, but the rules governing how energy and quantum fields are allowed to convert and interact. This alone changes the emotional texture of the universe. The world stops feeling like a collection of solid things lit by something else. Instead, it begins to feel like a shifting economy of excitations and interactions, where what exists at any moment depends strongly on the available energy and the conditions of the background. At extreme temperatures, the vacuum itself is no longer a calm absence, waiting for objects to be placed inside it. It becomes an arena of intense possibility, a region in which fields can be excited, particles can emerge, and stability becomes temporary. That temporary quality matters. At low temperatures, many familiar structures are durable. Atoms last, molecules last. Crystals hold their shape. Living cells go about their complicated business with astonishing confidence. But when the temperature becomes extreme, duration shrinks. Particles that are stable in cooler conditions may no longer remain stable in the same way. Reactions proceed rapidly. Creation and destruction balance and rebalance. Identity becomes statistical rather than permanent. The universe starts looking less like a museum of objects and more like a storm of processes. There is something important here about the word particle itself. In everyday speech, particle sounds like a tiny pebble, a miniature grain, a little indivisible bit of something. Modern physics has long since moved beyond that simple picture, even though the word remains. A particle in quantum theory is not best imagined as a hard dot waiting to be photographed like a grain of dust. It is better understood as an excitation of a field, a quantized disturbance with certain measurable properties. That description is already quite abstract, but it becomes indispensable at high energies. The hotter the system, the less helpful the pebble image becomes. What exists are not tiny marbles bouncing around inside a box, but highly energetic quantum excitations interacting according to the allowed symmetries and couplings of the theory. Even light changes character under that view, or perhaps it is better to say our understanding of it changes. In ordinary language, light is what illuminates. It shines, warms, reflects, and travels. In high-energy physics, light belongs to a broader family of field excitations. It is radiation, yes, but in a quantum framework it behaves with a particular aspect as well. At high enough energies, the practical distinction between matter and radiation becomes increasingly contextual. Both are manifestations of underlying fields. Both participate in thermal distributions. Both can transform through interaction when the conditions allow. As the temperature rises, wavelengths associated with the dominant excitations become shorter. This means that the physics becomes sensitive to smaller and smaller scales. A cool thermal bath mostly concerns itself with longer, gentler modes. A very hot one probes more deeply. It sees finer structure. It is as though increasing temperature sharpens the universe's microscope, forcing it to inspect details that remain irrelevant at lower energies. This is one reason extreme heat reveals hidden layers of reality. It is not just more violence, it is finer interrogation. And yet this sharpening comes with a price. In ordinary quantum theory, one can probe smaller distances with higher energies while still assuming a background spacetime that remains smooth and classical enough to support the whole setup. That assumption is not absurd. It works very well. But near the Planck regime, the energy needed to examine such tiny scales becomes so immense that the geometry of spacetime itself can no longer be treated as passive. The closer you look, the more the stage begins to answer back. This is where the blurring becomes especially profound. We're no longer merely watching particles interact in space. We're approaching conditions where the distinction between the contents of the universe and the geometry containing them becomes unstable. In general relativity, energy and momentum influence spacetime curvature. In quantum theory, fields and their excitations fluctuate. If those two truths must operate together at full strength, then the geometry itself may become subject to quantum uncertainty. Space is no longer just a fixed grid of positions. It may acquire its own microscopic restlessness. Physicists sometimes use evocative language here, speaking of spacetime foam or fluctuating geometry. These phrases are not final descriptions, but they capture the central intuition. At sufficiently small scales and high energies, smoothness may be an approximation rather than a fact. Just as the surface of the sea looks calm from far away but reveals turbulence and structure at closer range, space-time may appear continuous on large scales, while becoming jittery or quantized in some deeper microscopic account. If that is so, then asking precisely where a particle is, or exactly what path light takes, may become a much less straightforward question than it is in lower energy physics. This does not mean that the universe becomes lawless. It means our current language begins to lose its sharp edges. A particle requires a space-time setting in which concepts like position, momentum, and propagation are meaningful. Light requires a geometry through which it travels. Temperature itself requires a notion of degrees of freedom and energy distribution. But if the background geometry is fluctuating in a quantum way, then all of these notions must be handled with greater care. The blurring is not a failure of nature, it is a failure of simple categories to remain separate. There is a useful way to think about this without becoming too tangled in formalism. Imagine trying to describe a stormy ocean using the vocabulary of a still pond. The words are not wrong exactly. Water is still water, waves are still waves, but the conditions are so different that the old calm language no longer captures the reality well. Near the Planck regime, we are attempting something similar with the universe. We use words like particle, field, light, space, and time because they are the tools we have, but the domain itself may require a deeper vocabulary not yet fully agreed upon. One of the more intriguing possibilities suggested by high-energy theory is that distinctions among the fundamental forces may also become less rigid at sufficiently high energies. In ordinary life, gravity feels separate from electromagnetism, and both feel separate from the forces governing nuclear interactions. We learn them as different kinds of influence, each with its own domain and character. Yet modern particle physics already shows that some distinctions, which appear absolute at low energies, become unified under higher energy conditions. Forces that seem separate can emerge from a more symmetric origin, once the universe cools and symmetry is broken. This suggests that the early hot universe may have been governed by a more unified structure than the one we now observe. That possibility deepens the blurring further. Not only do matter and radiation exchange roles with increasing ease, not only does space-time itself threaten to become quantum and fluctuating, but even the separate identities of the interactions may trace back to a simpler, hotter unity. The cooler universe is a differentiated universe. It is one in which distinctions have crystallized. The hotter universe may be more symmetrical, more compressed, and less segmented into the categories we inherited later. There is something almost biological about that progression. Development often begins in undifferentiated forms and proceeds toward specialization. The early universe may have done something analogous. As it cooled, distinctions sharpened. Particles acquired familiar masses and stable identities. Forces diverged into the versions we observe. Bound structures became possible. Complexity emerged. To look backward toward higher temperatures is to watch those distinctions dissolve again, not into chaos exactly, but into a state that is more unified and less articulated. At this point, one might reasonably ask whether the word blur is really appropriate. After all, the mathematics of these theories can be extremely precise in the regimes where they apply. The answer is that blur here does not mean vagueness in prediction, where theory is secure. It means that the categories themselves cease to be sharply separable as we approach a regime beyond present confirmed theory. Light and matter are both manifestations of quantum fields. Fields and particles are different aspects of one framework. Geometry is no longer safely classical. Interactions may have shared origins. The deeper we go, the less the universe resembles a tidy inventory, and the more it resembles an interwoven whole. This is one of the reasons the Planck temperature is so important conceptually. It sits at the threshold where the blurring becomes impossible to ignore. Lower down the ladder, we can still speak meaningfully of extremely hot particle baths, plasmas, quark-gluon states, and early cosmic conditions within a framework that separates quantum matter from classical gravity, or at least postpones the conflict. Near the Planck scale, postponement no longer works. The collision between frameworks becomes unavoidable, and once that happens, even ordinary questions become harder to phrase. What is the smallest meaningful distance? What is the shortest meaningful time interval? What counts as a particle if localization itself becomes subtle? Can light still be said to travel along definite null paths if the geometry is fluctuating? Can temperature be cleanly defined if the underlying degrees of freedom are not those of particles on a fixed background but something more primitive? These are not decorative questions. They are the natural consequences of pushing known physics to its hottest and most compressed edge. There is a temptation to imagine this edge as a kind of bright final fire, a last furnace where everything glows more intensely than before. But that picture, while dramatic, is still too anchored in ordinary intuition. The real strangeness is not brightness, but instability of description. The universe does not merely get hotter, it becomes harder to parse. Concepts that once seemed separate begin folding into each other. The architecture of explanation becomes crowded. This helps explain why so many candidate theories of quantum gravity sound unusual even by the standards of modern physics. Some suggest that space-time is not fundamental, but emergent from deeper relations. Some suggest that geometry is quantized. Some suggest that our ordinary sense of locality itself must be rethought. These ideas are not generated because physicists enjoy making reality inconvenient. They arise because the Planck regime demands some account of what remains when particles, light, and space can no longer be treated as neatly distinct ingredients arranged on a classical stage. Still, it is worth staying grounded. Although the full theory is missing, the broad lesson is already clear. The familiar world is a cooled and simplified outcome. It is what the universe looks like after distinctions have settled enough for stable objects and clean categories to emerge. Extreme temperature peels that simplification away. It returns the cosmos toward a condition where identity is more fluid, conversion more rapid, and even the background less fixed than common sense would ever suspect. In a way, this makes the hot early universe feel less like a place and more like an argument not yet finished, a region where the terms themselves are still being negotiated. Matter has not fully become matter in the durable everyday sense. Light is not just what streams between objects but part of a thermal sea exchanging constantly with other excitations. Space may not yet be the calm geometry within which events occur, but part of the very problem under investigation. Everything is present, but nothing is final. That is a difficult state to picture, which is why cosmology so often works through careful analogy and patient abstraction, rather than literal visualization. We can picture stars, we can picture explosions, we can picture glowing plasmas. But once particles, light, and space begin to blur, visualization becomes less trustworthy. The mind wants to arrange little objects in a background, and the physics keeps objecting. The truth may be less like a scene, and more like a relation, less like a photograph, and more like a set of evolving constraints. Even so, there is one place where this blurring may not be merely theoretical extrapolation. If our best broad picture of cosmic history is correct, then the early universe itself passed through regimes increasingly close to this kind of fundamental indistinction. Not immediately in the sense of a complete understood model, because that is exactly what we lack, but in the sense that the thermal history of the cosmos leads backward toward conditions where our present categories become progressively less reliable. The young universe was not just hot enough to melt atoms or even nucleons. It was hot enough to make the whole notion of familiar structure feel premature, and that is where the story naturally turns next, because the blurring we have been describing is easier to grasp when placed in its most consequential setting. Not inside a machine, not inside a star, not in some isolated theoretical sandbox, but in the first fleeting instant of the universe's own history, when the entire observable cosmos may have lived in a state so compressed and so hot that all later distinctions were still waiting to emerge. When people hear the phrase "the first instant after the Big Bang," they often picture something like a fireball exploding into darkness. It is a natural image, and also a misleading one. The early universe was not a bomb going off inside an already existing empty room. It was not matter flying outward from a single point into surrounding space. The expansion involved space itself. The whole observable universe was once in a much denser and hotter state, and as it expanded, the conditions changed everywhere. That distinction matters because the first instant is already difficult enough without adding the wrong mental picture at the start. It also helps to be honest immediately about what we do and do not know. The phrase first instant sounds precise, but precision is exactly what becomes hard to maintain when talking about the earlier stage of cosmic history. The further back we go, the hotter and denser the universe becomes, and the more our tested theories are pushed toward their limit. There comes a point where the conditions approach the Planck regime, and there our current physics stops giving a complete reliable account. So when we discuss the first instant after the Big Bang, we are partly telling a story of increasing confidence as time moves forward. There are eras we understand reasonably well, eras we understand indirectly, and then there is the deepest beginning where our best theories are not yet unified enough to speak with full authority. That does not make the subject vague in an unhelpful way. It makes it interesting in a very specific way. We're not lost everywhere. We are lost at the exact place where quantum theory and gravity must both matter at once. Once the universe cools even a little beyond that most extreme beginning, our footing improves dramatically. So the first instant is not a simple clear frame from a cosmic movie. It is more like the edge of a photograph where the image fades, because the camera itself was not built for that light. Still, there are good reasons to think the early universe passed through an unimaginably hot, dense state. The evidence for cosmic expansion is strong. The cosmic microwave background tells us the universe was once far hotter and more uniform than it is now. The observed abundances of light elements fit beautifully with models of early cosmic nucleosynthesis. Large-scale structure makes sense within a universe that expanded and cooled over time. None of this tells us with certainty what happened in the very first Planck scale moment, but it gives us overwhelming reason to take the hot early universe seriously. So what was that earlier stage like, at least as far as we can responsibly describe it? The first thing to understand is that it was not a world of objects. There were no stars, no atoms, no planets, no light travelling through transparent space in the way it does now. There were not even stable protons and neutrons in the familiar sense. At least not at the earliest extreme temperatures. The universe was a thermal system of staggering density and energy, filled with a rapidly changing mix of quantum fields and particles in continual interaction. If that sounds less like a place and more like a process, that is because it was. At such high temperatures, familiar distinctions had not yet settled. Matter and radiation exchanged roles freely. Particles could be created and destroyed in collisions. The vacuum was not an empty stage, but a highly active environment. The forces of nature may not yet have had the distinct low-energy forms we know now. As the universe expanded and cooled, one thermal threshold after another was crossed. Each threshold changed what kinds of structures could exist, what interactions dominated, and what ingredients remained abundant. This is why early cosmology is often told as a cooling sequence. We do not begin with a universe already full of things and then ask how they moved around. We begin with a very hot state and ask what could survive there. At the highest temperatures, almost nothing familiar could. There is too much energy, too much interaction, too little stability. As the temperature falls, new possibilities open, symmetries break. Particles acquire familiar properties. Bound states become possible. The universe does not become more interesting because it gets hotter. In many ways, it becomes more structured because it gets cooler. That can feel slightly backwards at first. Heat often seems lively and exciting. Cold seems quiet. But in cosmology, extreme heat is a kind of simplification through violence. It strips away durable structure. The very early universe was not rich in the everyday sense. It was rich in energy, but poor in settled complexity. The atoms that later fill the world could not yet exist. chemistry was impossible. Even nuclei had to wait. The first instant after the Big Bang was not the beginning of familiar things. It was the beginning of the conditions from which familiar things could eventually emerge. The phrase Big Bang itself can cause trouble here because it sounds like a brief event after which the interesting part is over. In reality, the expansion and cooling that followed are the whole story. The early universe did not simply explode and stop. It evolved. Temperature changed. Density changed. The balance between radiation and matter changed. Tiny fluctuations in density, small differences from place to place, later grew under gravity into the structures that would become galaxies and clusters. The first instant matters, but not because everything meaningful happened all at once. It matters because it set the initial terms of a very long unfolding. Now, when cosmologists speak cautiously about the earliest moment they can somewhat discuss, they often mean the era after the Planck time. That is not because something magical happens exactly at that boundary in a cinematic sense. It is because before that scale, our current theories cannot be trusted to give a complete account. During that earliest Planck era, the temperature would have been around the highest natural scale we talked about earlier. Energy density would have been so extreme that quantum effects of gravity could not be ignored. Space-time itself may have been subject to fluctuations so strong that the classical picture of smooth geometry breaks down. This is the region where the phrase first instant becomes most treacherous. We can say that if one extrapolates the known expansion backward, one approaches a state of increasing temperature and density. We can say that near the Planck regime the known theories become incomplete. We can suspect that a deeper theory of quantum gravity would describe what really happened there, but we do not yet possess that final tested theory, so there is a sense in which the true first instant remains hidden, not because it is mystical, but because the required physics is unfinished. Once the universe expands beyond that deepest unknown zone, our picture improves. The temperature is still appallingly high by any normal standard, but now we can begin speaking in terms of known particle physics with more confidence. The universe is filled with an intense hot bath of particles and radiation. Collisions happen constantly. Creation and annihilation processes remain common. Everything is packed close, energetic and dynamic. There is no room yet for atoms or anything like ordinary matter, but the description becomes more recognizable. We are back within the broad territory of quantum fields and thermal distributions, even if the conditions are extreme. One of the striking features of such an early universe is how uniform it appears to have been on large scales, and yet not perfectly uniform. That tiny imperfection matters enormously. If the universe had been perfectly smooth forever, there would be no stars, no galaxies, no planets, no observers. Structure requires imbalance, however slight. Somewhere in the early history of the cosmos, tiny fluctuations in density were present. They were small enough that the universe remained extraordinarily uniform overall, but real enough that gravity could later amplify them. A slightly denser region pulls in more matter, becomes denser still, and over vast stretches of time this quiet imbalance grows into cosmic architecture. This means that the first instant after the Big Bang was not only about heat, it was also about seeds. The universe had to begin hot and dense, yes, but it also had to contain the right sort of minute irregularities for all later structure to emerge. The origin of those fluctuations is one of the deep questions in cosmology. Some theories tie them to quantum fluctuations stretched to cosmic scales during a hypothesized era of rapid expansion known as inflation. Inflation is a powerful and widely discussed idea because it helps explain several puzzling features of the observable universe, including its large-scale flatness and uniformity. But even there, as with all early epoch cosmology, the closer we move to the deepest beginning, the more careful we must be about what is solidly known and what remains an active area of theoretical work. It is useful to think of the early universe as a sequence of eras rather than a single explosive scene. In the earliest unknown region, quantum gravity dominates, and our present theories lose their full authority. Slightly later, if inflation occurred, the universe may have undergone an extraordinary burst of accelerated expansion. After that, the energy driving that phase would have been converted into a hot bath of particles, repopulating the universe with the ingredients of conventional high-energy physics. From there, as expansion continued, the temperature dropped through one threshold after another. Particle species that were easily created at higher temperatures became rarer once the thermal bath no longer carried enough energy to produce them abundantly. Symmetries broke, familiar distinctions emerged. Eventually, protons and neutrons became durable enough to matter. Later still, nuclei formed. Much later, atoms. Later again, stars and galaxies. Seen that way, the first instant after the Big Bang is less like the opening blast of a story and more like the first line in a long technical recipe. The rest follows from how the ingredients cool, interact and settle. That may sound less dramatic, but in truth it is much more impressive. The early universe did not just produce spectacle, it produced conditions under which physical law could gradually generate complexity. There is another misconception worth clearing away here. People sometimes imagine that because the early universe was so hot and dense, it must have been chaotic in the simple everyday sense, like a room after a severe argument and a very careless moving company. But high temperature does not automatically mean conceptual disorder. In fact, some of the deepest puzzles in cosmology arise because the early universe seems to have been in certain respects remarkably simple and special. Its large-scale smoothness, its low gravitational entropy compared with what came later, and the precise conditions that allowed time to have its arrow are all part of the mystery. The beginning was not merely hot, it was hot in a highly consequential way. That phrase, low gravitational entropy, may sound like the sort of thing one should only mention if one is prepared to spend a weekend explaining it, but the basic point is important. Matter distributed very uniformly through space can correspond to low entropy from the gravitational point of view, because gravity tends to amplify clumping. A universe full of stars, black holes, and highly clumped structures is in some ways a more gravitationally disordered state than a smooth early universe. This means that the beginning was not just a furnace, it was a furnace with special large-scale conditions. That specialness is one of the reasons the origin of the arrow of time remains such a deep question. All of this should make us cautious about casual statements like the universe began as an explosion. It began, as far as our current evidence suggests, in a hot, dense, evolving state, with special conditions whose deepest description likely requires physics beyond our present complete theories. That is less catchy, admittedly, but much closer to the truth. The price of accuracy is sometimes the loss of a good poster slogan. Even so, there is room for awe without exaggeration. The early universe was hotter than any star we see now, hotter than any supernova remnant, hotter than any laboratory plasma. For a while it was so hot that the familiar ingredients of the present universe had not yet settled into their current form. Every atom in your body, every rock on Earth, every cloud, sea and living thing traces back through that thermal history. The calm room you know tonight is part of a cosmos that began in a condition so extreme that even the words hot and dense are only the start of the description. There is also something quietly humbling in the fact that the first instant may never be fully describable using only the theories we already have. Human knowledge has gone astonishingly far. We can reconstruct the thermal history of the universe across vast stretches of time. We can detect ancient light still washing through space. We can calculate element abundances, model galaxy growth, and infer the presence of matter we cannot see directly. And yet at the very beginning, at the point where gravity and quantum theory must finally make peace, we still stand outside the room listening at the door. That is not failure. It is simply the frontier. The first instant after the Big Bang is where cosmology becomes a test of our most ambitious theoretical ideas. Any candidate theory of quantum gravity must eventually answer to that beginning. it must explain what a first instant even means, whether time itself had a meaningful earlier and later there, whether space-time emerged from something deeper, and how the hot evolving universe we can describe later came out of that deeper regime. Until then, the earliest instant remains partly hidden, but not wholly disconnected from us. Its consequences are everywhere. The expansion continues. The cosmic microwave background remains as a cooled afterglow of the hot early universe. The large-scale distribution of matter still carries traces of ancient fluctuations. The abundance of light elements still reflects nuclear processes from the first minutes. The universe keeps records in the only way it can, by becoming what it became. And that is perhaps the most useful way to think about the first instant. Not as a bright point we can photograph, but as a beginning inferred from everything that followed. We do not see it directly. We read it through consequences. We reconstruct it from fossils of radiation, from elemental patterns, from expansion, from structure. The beginning is written into the present, though in a language that takes a great deal of patient physics to read. As we move on, the question becomes less about the beginning as an event and more about the meaning of its heat. If the early universe may have approached the highest temperature scale known to theory, then we need to ask what that really tells us. Not just that the beginning was unimaginably hot, but that this hottest possible regime may reveal something about the architecture of reality itself, and about whether anything in the modern universe could ever come close to such conditions again. That brings us to a question that feels almost inevitable once the early universe has entered the picture. If the Planck temperature belongs to that first extreme phase of cosmic history, could anything ever reach it again? Could nature produce it somewhere in the modern universe? Could a black hole, a collision, a future machine, or some still unknown process recreate the hottest regime physics can meaningfully name? Or was that temperature a one-time privilege of the beginning, a brief condition tied to the birth of the cosmos and not something the universe is likely to revisit in any accessible way? The first thing to say is that nothing we ordinarily encounter comes remotely close. That may sound obvious, but it is worth stating because the word hot tends to flatten our sense of scale. A blast furnace is hot, lightning is hot, the surface of a star is hot, the centre of a star is much hotter, a supernova is hotter still. The matter created in high-energy particle collisions is hotter again. Each of these feels dramatic, and each deserves respect, especially if one has any wish to remain physically coherent. But the Planck temperature is so far beyond all of them that the comparison is almost unfair. It is not like comparing a bonfire to a volcano. It is more like comparing the warmth of a kettle to the temperature history of the universe itself. So the honest first answer is no, not in any ordinary physical setting known to us. No star burns at that temperature. No naturally occurring region of modern space is expected to sit stably in that regime. No laboratory on Earth has come anywhere near it in a sustained, meaningful sense. Even the most violent events we know, exploding stars, matter plunging into compact objects, powerful particle collisions, remain far below that threshold in any practical description. This is not because the universe lacks violence. It is because the Planck scale is not merely very high. It is the scale where the whole architecture of present theory starts protesting. Still, there is a second answer, and it is more interesting. The question, could anything ever reach it again, depends on what kind of again we mean. If we mean could the modern universe as a whole return to such a condition naturally, then under the broad picture of cosmic history we currently use, the answer appears to be no. The universe has been expanding and cooling for a very long time. Its large-scale story since the hot early epoch has been one of thermal decline, not return. Local pockets of enormous energy can still form, but the universe overall is moving away from that original dense hot state, not toward it. If we mean could some tiny local region be driven to comparable conditions, then the question becomes more subtle. In principle, one can imagine packing extraordinary amounts of energy into extraordinarily small regions. Particle accelerators already do this on modest scales relative to the cosmic extremes. They do not heat a large object in the familiar sense. They produce tiny, brief, intense states in which energy density becomes very high. That is how one gets the hottest temperatures ever created by human beings, if one chooses to use temperature language for such fleeting microscopic events. So the basic strategy is not absurd. You do not try to warm a mountain until it glows with fundamental physics. You focus stupendous energy into a minuscule volume for an absurdly brief time. But once the target is the Planck regime, the challenge becomes almost laughably severe. It is not merely an engineering problem in the sense of needing a bigger machine. It is a problem of scale so extreme that even the phrase bigger machine starts sounding like a village response to a cosmological difficulty. To approach the Planck temperature, one would have to probe energies and localization scales where gravity can no longer be ignored. At that point, the act of concentrating the energy becomes entangled with the geometry of space-time itself. The machine is no longer just a device operating within known physics. The attempt would carry you to the edge of the very physics you're trying to explore. That leads to one of the strangest features of this question. To reach the Planck regime is not like aiming for a hotter plasma within an otherwise stable theoretical framework. It is to aim directly at the point where the framework changes. So the obstacle is not just practical, it is conceptual. Even if a civilization unimaginably more advanced than ours tried to engineer such conditions, the meaningful description of what they were making would require precisely the new theory that the Planck regime is asking for. One might say the universe is hiding its deepest layer behind a lock whose key must be forged from the very metal inside the locked room. Black holes naturally enter the conversation here, because whenever gravity and extreme energy appear in the same sentence, black holes soon arrive as though they had been waiting for the cue. Could black holes somehow recreate Planck temperature conditions? The answer depends on what aspect of black holes one is considering. If matter falls into a black hole, it can become extraordinarily hot in the surrounding accretion disk before crossing the horizon. Gravitational energy is converted into heat and radiation with great efficiency. These environments are among the brightest and most energetic in the universe. But even there, we are not talking about the Planck regime in the full sense. The temperatures are impressive and sometimes savage, but still not of the order that would force quantum gravity into center stage. What about the black hole itself? Black holes have a temperature in a very deep theoretical sense associated with Hawking radiation. This is one of the most remarkable insights in modern physics, because it combines gravity, quantum effects, and thermodynamics in a way that still feels slightly audacious even after decades of discussion. But large astrophysical black holes have extremely low Hawking temperatures, far below any ordinary thermal environment. They're colder, not hotter, in that sense. Only very tiny black holes would have high Hawking temperatures. As a black hole loses mass, its temperature rises. In principle, an extremely small black hole nearing its final evaporation could become fantastically hot. And here, for the first time, we are at least pointing in the right direction. Yet even this becomes difficult exactly where it becomes interesting. A black hole shrunk to the point where its temperature approached the Planck scale would itself be entering a regime where our current theories are not fully sufficient. The final stages of black hole evaporation are expected to involve precisely the kind of quantum gravitational uncertainty that defines the Planck frontier. So once again we find the same pattern. We can reason toward the boundary. We can see why it matters. But the exact description at the edge is where present theory runs thin. There is a certain consistency to that, and perhaps even a kind of cosmic teasing. Whenever physics gets close to the Planck regime, whether through extrapolating backward to the earliest universe or forward to the last stage of black hole evaporation, the same unfinished business reappears. The details are hidden in the place where gravity and quantum behavior must be understood together. Could particle collisions in principle do it? In a very abstract sense, yes, if one imagines concentrating enough energy into a tiny enough region. But the word principle is doing a heroic amount of work there. The energies required are so far beyond anything our current technology can provide that ordinary scaling arguments become almost comic. One does not simply build a larger accelerator and hope for the best, any more than one builds a taller ladder and expects to brush the moon. The gap is not a matter of determined budget meetings and optimistic committee notes. It is immense. There is also a deeper issue. At sufficiently high collision energies, gravity itself becomes part of the process in a non-negligible way. Depending on the true underlying theory, one might not get a neat, clean window into smaller distances at all. One might produce exotic gravitational phenomena instead. Some speculative ideas even suggest that above certain scales, attempts to localize energy too strongly could lead to tiny black hole formation, rather than straightforward access to ever smaller structure. The details depend on theories not yet confirmed, but the lesson is clear enough. Near the Planck regime, the universe may stop behaving like an obedient object of inspection and start reshaping the very experiment. This is one of the reasons the question could anything ever reach it again is both physical and philosophical. It sounds like a question about temperature, but in truth it is a question about access. Can a later cooler universe ever reopen the deepest furnace of its own birth? Can intelligence inside the cosmos engineer a return to the most fundamental conditions from which the cosmos emerged? Or is the Planck era not just historically first, but effectively inaccessible except through indirect theoretical understanding? Speculative cosmology offers a few more exotic possibilities. Some models of the very distant future, or of cosmic cycles, or of new inflationary pockets spawning from quantum processes, imagine circumstances where regions of space-time might again reach extraordinarily high energy densities. But one has to be careful here. These are not confirmed pictures of the modern observable universe deciding to turn the thermostat back to the beginning. They are theoretical scenarios at the edge of cosmological imagination. Useful, perhaps, provocative certainly, but not firm grounds for declaring that the Planck temperature will casually make a comeback somewhere next Tuesday. There is also the possibility that the early universe itself was not unique in a strict absolute sense. Some cosmological models entertain bouncing universes, cyclic histories, or broader structures in which hot dense beginnings occur more than once or in more than one region. If any of those pictures turned out to describe reality, then the Planck regime might not belong only to one primordial moment, but again, that would not mean the modern, cooled cosmos as we experience it is likely to regenerate the same condition in any accessible way. It would mean that the deeper architecture of reality admits such beginnings more than once. That is a different kind of again. At a more practical level, one of the reasons the early universe could reach such extreme temperatures is that the entire observable cosmos was once compressed into conditions of extraordinary density. The universe did not need to build a machine to achieve the Planck regime. It was the machine, if machine is the right word for a newborn space-time still sorting out its own terms. Local processes in the later universe are constrained in a way the global beginning was not. Stars form within an already expanded space. Black holes form from matter in a universe whose large-scale temperature is low. Even the most violent modern events are local disturbances against a cooled cosmic backdrop. The beginning was different, because it was not local against a background. It was the background. That difference may be the most important point of all. The Planck temperature belongs naturally to a question about origin, not merely about extremity. It is not just the highest rung on a scale of hotter and hotter things. It is the regime in which the distinction between thing and background starts to break down. That is why recreating it later is so hard to think about. To recreate it would be to recreate, even locally, conditions in which the stage and the actors are both caught up in the same unresolved physics. Still, human beings are stubborn creatures, and part of the charm of science is that it keeps asking unreasonable questions. Could something ever reach it again? Probably not in the ordinary modern universe as we know it, not in any stable, accessible astrophysical environment, not with any technology remotely imaginable from our present position. Could aspects of physics near that scale appear in extreme gravitational situations, in the final fate of tiny evaporating black holes, or in other speculative contexts? Perhaps, though always with the warning that those are precisely the places where our present theories need help. Could the broader cosmos contain processes or domains where such conditions occur beyond our observable reach? It is possible, but not established. The deeper answer, then, is that the question reveals why the Planck temperature matters. If it were merely an impractically large number, we could shrug and move on. But because it names the point where present theory breaks into unfinished pieces, asking whether it can be reached again becomes a way of asking whether the deepest origin conditions of reality are repeatable, accessible, or forever mostly known through inference. That is a much richer question than it first appears. There is even a quiet emotional difference between a universe that can and a universe that cannot revisit its own beginning conditions. If it can, then the most profound furnace of creation is not wholly sealed in the past. It remains in principle part of the living repertoire of reality. If it cannot, then the Planck era stands as something more singular, not only first in time, but categorically different from everything that followed. Either way, the boundary tells us something powerful about the structure of the cosmos. It tells us whether the deepest laws are merely historical in their most extreme expression, or whether they remain dynamically available under the right impossible conditions. For now, the safest conclusion is modest. The Planck temperature is not something the present universe casually produces. The modern cosmos contains astonishing heat, but not that kind of heat in any confirmed reachable setting. The early universe remains the main stage on which such conditions are thought to have played out. Later processes may gesture toward the same frontier, but only at the places where current theory becomes uncertain and where speculation begins to share the room with calculation. And perhaps that is exactly as it should be. The hottest possible temperature is not really important because we expect to bottle it. It matters because it illuminates the edge of our understanding. It tells us what sort of theory the universe still demands from us. It tells us that the beginning was not merely hot in a dramatic sense, but hot enough to expose the unfinished architecture of fundamental physics. And once we see that clearly, the next step is almost unavoidable. We have to ask what this extreme limit, whether repeatable or not, actually reveals about the nature of reality itself. By this point, the Planck temperature may sound like the kind of idea that exists mainly to make human beings feel small and thermometers feel underqualified. It is certainly good at both. But its real importance is deeper than scale alone. The hottest possible temperature matters because of what it reveals about the structure of reality. It is not simply the top of a chart. It is a clue, a boundary, a statement about how the universe is built, how our theories divide the world, and where those divisions stop working. In that sense, the Planck temperature is less like a final answer and more like a message from nature, saying you have understood a great deal, but not yet the whole thing. One of the clearest lessons it offers is that the universe seems to contain natural scales that are not based on us. Human beings are very fond of measuring the world using local conveniences. We divide the day into hours. We build rulers. We set temperature scales according to water, weather, or historical habit. All of that is practical and perfectly sensible for ordinary life. But the Planck temperature does not care about any of those conventions. It is not hot because our bodies would dislike it, though that is putting it very mildly. It is hot because the fundamental constants of nature combine in a way that defines a thermal regime where known descriptions become incomplete. That is a very different sort of significance. This tells us something important right away. Reality is not just a continuous blank canvas onto which any values can be painted without consequence. It has joints. It has structure. There are scales where certain ideas become appropriate and scales where they do not. There are ranges where a theory works comfortably and ranges where it starts to strain. The Planck temperature is one of the clearest examples of this. It says the universe is not infinitely transparent to the methods we currently use. Push heat far enough, and the world does not merely become more extreme, it becomes conceptually different. That is a remarkable thing to learn from temperature, a quantity that at first seems so modest and familiar. Heat is one of the earliest physical experiences we ever have. We know it as babies long before we know any words for it. We know warmth, chill, the comfort of blankets, the sting of something too hot to touch. And yet if we follow that ordinary experience all the way upward through physics, it leads to one of the deepest frontiers in science. That alone says something beautiful about reality. The everyday world and the most fundamental world are not separate subjects. They are connected by scale. The Planck temperature also tells us that our best theories are astonishing but incomplete. This is not a criticism of science. It is one of science's great strengths that it can identify its own boundaries with precision. Quantum theory explains the behavior of the microscopic world with extraordinary success. General relativity explains gravity, and the large-scale structure of space-time with extraordinary success. Neither is a minor achievement. Each is among the most powerful intellectual frameworks human beings have ever built. And yet the existence of the Planck regime tells us that these two triumphs do not yet form a final union. There is a domain where both must matter fully at once, and there our present understanding runs thin. That fact reshapes how one thinks about reality itself. It suggests that the categories we use now, particles here, space-time there, fields on one side, geometry on the other, may be provisional rather than ultimate. They work magnificently in the domains where they were tested, but perhaps they are not the deepest language. Perhaps they are emergent descriptions, late-stage simplifications that arise once the universe cools and settles enough for distinctions to sharpen. If so, then the Planck temperature is telling us that underneath the familiar architecture of modern physics, there may be a more unified layer we have not yet fully grasped. There is something both humbling and reassuring in that. Humbling because it reminds us that even our most elegant theories may be intermediate truths rather than the final floor of the house. Reassuring because it means the universe still has more to teach. There remains genuine discovery ahead, not just technical refinement. The Planck scale is one of the places where reality still keeps part of its machinery behind a curtain. Another thing the hottest possible temperature tells us is that space-time may not be as fundamental as it appears. This is one of the strangest and most important hints in modern theoretical physics. In daily life and in much of standard science, space and time feel like the unquestioned background. Things happen somewhere and sometime. Objects move through space. Events unfold in time. Even relativity, for all its radical shift, still gives us a space-time framework. Curved and dynamic perhaps, but still the stage on which physical processes occur. The Planck temperature suggests that this stage may itself have a deeper origin. That is a difficult idea to absorb because the mind is accustomed to imagining reality as things located in a pre-existing arena. If the arena itself is emergent, then our basic picture of existence changes. Space may not be the container we thought it was. Time may not be the river we instinctively imagine. At sufficiently extreme conditions, the very notions of distance and duration may depend on deeper structures from which they arise. If that is true, then the Planck temperature is not merely the hottest possible thermal state. It is a sign that the framework of reality may be layered in a way our senses never prepared us to expect. This also feeds into a more philosophical lesson. The universe does not seem to be built from the categories that feel most natural to us. It is built from structures that often reveal themselves only through careful mathematics, patient experiment, and a willingness to let go of comfortable images. Human intuition evolved for stones, weather, faces, and firewood. It did not evolve for quantum fields or non-Euclidean geometry, or the thermal history of the early cosmos. The fact that we can nevertheless discover such things is one of the quiet marvels of science. The fact that we still meet boundaries like the Planck scale is a reminder that understanding is a process, not a possession. The Planck temperature also says something about unity. Much of the history of physics has been a gradual discovery that seemingly separate phenomena belong together. Falling apples and orbiting moons turned out to share the same gravitational law. Electricity and magnetism turned out to be aspects of one framework. Space and time turned out to be interwoven. Matter and energy turned out to be deeply related. Quantum theory and relativity each pulled different pieces of reality into broader coherence. The Planck regime hints that this pattern may not be finished. The distinction between matter, radiation, force, and geometry may itself be part of a cooler, lower energy view of a deeper unity. This is one reason extreme temperature can be so revealing. Heat strips away complexity. It removes stable bound structures and exposes more primitive behavior underneath. In the early universe, high temperature prevented atoms from forming. Higher temperature prevented even nuclei from remaining bound. At still more extreme scales, the interactions we distinguish now may have been less distinct. The hotter the universe, the fewer familiar layers it could sustain. That means the Planck temperature points toward a state where reality may have been maximally stripped of later structure, a condition closer to the raw grammar of existence. There is a risk, of course, of making that sound too mystical. The point is not that the Planck regime reveals a secret spiritual essence of the cosmos wrapped in blazing light and deep thoughts. The point is more disciplined and more interesting. It reveals where known categories fail, and therefore where deeper explanatory structure must exist. That is not poetry replacing physics. It is physics leading to deeper questions. Those questions touch the nature of beginnings. If the universe once passed through or near the Planck regime, then the hottest possible temperature is tied to origin. It becomes part of the story of why there is a large, cool, structured cosmos at all. This makes the Planck temperature not just a boundary in theory, but a historical clue. It reminds us that the world around us is not the default state of reality. The stable room, the sleeping house, the planet beneath our feet, the stars overhead, all of this belongs to a cooled and differentiated phase of cosmic history. The universe was once much less settled. That realization changes the emotional meaning of the ordinary world. The calm of familiar existence is not primitive. It is achieved. It is what becomes possible after expansion, cooling, symmetry breaking, structure formation, and a long, long thermal descent. Reality, at its deepest accessible beginning, may have been less like a world full of things, and more like a condition from which things eventually emerged. The Planck temperature is one of the markers of that transformation. It tells us that the familiar is late, not early. It also says something about limits in science more broadly. Limits are sometimes treated as disappointments, as though they were merely places where knowledge stops. But the best physical limits are not blank walls. They are informative boundaries. The speed of light tells us how space-time is structured. Absolute zero tells us something about thermal motion and the organization of low-energy states. The Planck temperature tells us that there is a point beyond which our current division between quantum theory and gravity cannot hold. In each case, the limit teaches. It is not a dead end. It is a signpost. This way of thinking is useful because it keeps the Planck temperature from becoming just an impressive number in a science documentary voice. Impressive numbers are easy to generate. Nature has large and small quantities everywhere. What matters is interpretation. Why this scale? Why this significance? Why does this number mark a conceptual frontier rather than just a statistical curiosity? The answer is that it encodes the meeting point of the deepest constants we know, and therefore points directly at the unfinished work of theoretical physics. There is another reality lesson hiding in that. The universe is understandable in layers. We do not need the full theory of quantum gravity to build a bridge, predict a chemical reaction, or navigate using satellites. Reality allows partial understanding. It permits domains of effective truth. This is one of the reasons science has been so successful. We can understand a vast range of phenomena without already possessing the final theory of everything. The Planck temperature does not invalidate lower-level knowledge. It locates it. It tells us where it belongs in the hierarchy of description. That is a subtle but important point. When people hear that known theories break down at extreme scales, they sometimes imagine that everything becomes uncertain or suspect. But that is not how science works. Newtonian mechanics remains useful for everyday motion even though relativity is deeper. Chemistry remains real even though atoms have substructure. Thermodynamics remains powerful even though it emerges from statistical mechanics. Likewise, quantum field theory and general relativity remain magnificent within their proven domains, even if they are not the final combined account. The Planck temperature teaches not that lower-level understanding is false, but that it is situated. One could say that reality is generous enough to allow nested truths. That is a comforting thought for anyone who has ever worried that discovering a deeper level somehow erases the one above it. It does not. The existence of molecules does not make soup imaginary. The existence of quarks does not make tables fictional. The possibility that space-time is emergent does not make distance unreal in the room you're sitting in. It simply means that different scales ask for different descriptions, and the deepest scale may ask for the most radical revision of all. The Planck temperature also sharpens our sense of mystery in a productive way. Some mysteries are vague because we do not even know how to ask the right question. This one is better behaved. We know what the tension is. We know which theories are colliding. We know roughly where the collision matters. We know that a complete theory of quantum gravity must speak to this regime. That means the mystery is structured. It is not a foggy abyss where anything goes. It is a precise absence in an otherwise remarkably detailed map. There is a great deal of progress hidden in being able to say exactly what one does not yet know, and then there is the question of whether reality is fundamentally continuous or discrete. The Planck scale sits right in the middle of that ancient tension. Classical intuition prefers continuity. Space extends smoothly. Time flows smoothly. Energy can vary by any amount. Quantum theory already disrupted some of that picture by introducing quantized behavior into physical systems. The Planck regime raises the possibility that even space and time may not be smooth all the way down. If that turns out to be true, then the hottest possible temperature is part of the evidence that continuity itself may be an approximation, a large-scale convenience rather than an ultimate truth. That would be a profound shift. It would mean that some of the most basic features of how reality appears to us are emergent smoothing effects, not the final texture of the world. Much as a fabric can look continuous from a distance while revealing threads up close, space-time might appear smooth while being built from deeper, non-continuous structures. The Planck temperature does not prove that picture by itself, but it points directly toward the scale where that question becomes unavoidable. There is something pleasingly democratic about the way all this comes back to heat. Of all the roads to the foundations of reality, one of them begins with the ordinary human fact that things can be warm or cold. That road leads through thermodynamics, radiation, quantum theory, cosmology, and ultimately to the threshold where our current understanding breaks. A kitchen concept grows into a cosmic clue. That is exactly the sort of thing physics does best. It takes what feels local and reveals it to be universal. And perhaps the deepest lesson of all is this. Reality seems to be both more unified and more elusive than the human mind first expects. More unified because the same constants, the same laws and the same thermal history connect tea, stars, black holes, and the early universe. More elusive because each time we think we have reached the final simplicity, another deeper layer appears. The Planck temperature is one of those moments of reappearance. It tells us that the world is still holding back part of its most basic account. Not forever, one hopes, but for now. That hope matters. It gives scientific curiosity its forward motion. The Planck regime is not just a barrier to be admired from a distance. It is an invitation to continue. Somewhere beyond our present frameworks lies a description that can explain what becomes of matter, light, space, and time when the universe is pushed to its most extreme thermal edge. Whether that description comes from strings, loops, holography, emergent geometry, or some idea not yet properly born, the Planck temperature is one of the clearest signs that such a description must exist. So what does the hottest possible temperature tell us about reality? It tells us that nature has fundamental scales not chosen by us. It tells us that our most successful theories are powerful, but not yet complete. It tells us that space-time may not be the final stage we imagined. It tells us that the early universe lived in a regime closer to the raw foundations of existence than anything we now observe. It tells us that limits can be deeply informative, and it tells us that beneath the cool, structured world of late-time existence there may lie a more unified layer still waiting to be understood. That is quite a lot for one temperature to say, and perhaps it is enough for the mind to sit with for a while. Because once the hottest possible limit has revealed itself not merely as a number, but as a window into the unfinished architecture of the cosmos, the natural thing to do is not to force a conclusion, but to let the glow of that thought linger a little longer, the way a room holds warmth after the fire itself has gone quiet. And now we arrive at the quiet end of this long warm trail, a little farther along than when we began, having followed heat from the kitchen and the weather to stars, to collapsing matter, to the first age of the universe, and finally to that extraordinary upper limit called the Planck temperature. It is a strange place to end an evening, perhaps, with the hottest possible temperature still glowing in the mind. But there is something oddly calming about it too. After all the numbers too large to picture, all the states of matter too extreme to survive, all the theories that begin to strain and blur, what remains is not just the idea of heat, but the shape of a much bigger truth. The universe is layered. The familiar world sits on top of depths we only partly understand. And sometimes the best way to feel that clearly is not by staring at what is close and ordinary, but by letting the mind wander to the most distant edge of what physics can still meaningfully ask. There is a certain comfort in tracing such a question all the way through. At the start, the topic sounds almost exaggerated. The hottest temperature possible. It seems like the sort of phrase designed to provoke wide eyes and dramatic music. And if we are being honest, it does have a bit of that quality. But once you spend time with it, the drama settles into something more interesting. The Planck temperature is not simply the end of a contest over who can produce the most extreme furnace. It is not about winning a race against the sun or building a kettle capable of offending the very laws of nature. It matters because it reveals where our current understanding stops being comfortably complete. It is the place where the ideas that serve us so well for particles and fields on one side, and space and gravity on the other, can no longer live separate lives. That is quite a thing to discover while talking about heat. Most of the time, temperature feels like one of the least mysterious quantities in existence. You glance at a forecast, you touch a mug, you wonder whether the radiator is too high or whether the window should be left open a little longer. You ask whether the bath has cooled. You complain that summer has gone too far or winter has not gone far enough. Temperature lives in comfort and inconvenience, in weather and cooking, in wool socks and cold floors. It is almost embarrassingly ordinary. And yet that same idea, followed upward through physics with enough patience, leads straight to the frontier where space-time itself may no longer be describable in the old, smooth, familiar way. That is one of the small miracles of science. It takes a common experience and reveals that hidden behind it is a staircase into the foundations of reality. Along the way, we learn that heat is not just a sensation, but a measure of microscopic activity, of energy distributed among the hidden motions and internal possibilities of matter. We saw that as temperature rises, the universe begins peeling away its own layers. Molecules lose their bonds, atoms lose their electrons, nuclei lose their ordinary stability. Familiar particles reveal more fundamental ingredients beneath them. What feels like simple warming from a human point of view becomes, at more extreme scales, a kind of stripping down, a removal of structure, a forced honesty. Heat, in that sense, is not just about adding more. It is about revealing what remains when the comforts of stability can no longer survive. Then the ladder climbed higher. We moved from everyday warmth to lightning, to the surface of the sun, to the deep core of stars, to the violence of supernovae and the strange, brief infernos produced in particle collisions. And even those turned out to be only partial steps. For all their power, they still belong to a universe that has already cooled considerably from its beginning. The great surprise waiting beyond them was that the most intense thermal state was not likely to be found in some present-day object at all, but in the earliest chapter of cosmic history, when the whole observable universe was denser, hotter, and less settled than anything now common in nature. That realization alone changes the feel of the room around you, or at least I think it does. The bed, the wall, the air, the quiet rhythm of a late evening house, all of it belongs to a universe that was once too hot for atoms to exist, too hot for nuclei in the ordinary sense, too hot perhaps for space-time itself to remain a calm stage. The world we know is not the default condition of existence. It is the cooled result of a long descent. It is what becomes possible after expansion and settling and countless thresholds crossed in the right order. There is something very grounding in remembering that, not because it makes the room less real, but because it makes it more astonishing. It also reminds us that stability is not primitive, it is earned. The ordinary world is a late achievement of cosmic history. The atoms that build your body, the glass in a window, the oxygen in the air, the iron in blood, the calcium in bone, all of it belongs to a reality that had to cool and slow and organize itself long enough for such things to be possible. If the universe had remained too hot, nothing like the present world could exist. No chemistry, no planets, no oceans, no quiet nights, no listeners wondering how hot the universe once was while deciding whether they're quite sleepy yet. And that, perhaps, is part of the quiet emotional force of the Planck temperature. It marks not just an upper bound, but a contrast. There is the universe near its earliest, hottest, least differentiated state, and there is the universe here and now, cool enough for memory and language and tiredness and blankets. Somewhere between those extremes lies everything we call history. Not only human history, but stellar history, planetary history, chemical history, biological history. The enormous story of a cosmos becoming calm enough in places for complex things to last. Of course, part of what makes this topic linger in the mind is that it does not give us a neat final answer. If anything, it ends by sharpening the question. The Planck temperature tells us that our best theories are magnificent and unfinished. Quantum theory explains the small with extraordinary success. Relativity explains gravity and space-time with extraordinary success. But at the thermal edge where both must matter fully, the combined description is still missing. That absence is not a flaw in science. It is evidence that science is alive. There is still something real to discover. The universe has not yet been reduced to a solved puzzle in a cabinet. It remains, at its deepest levels, a working conversation. I find that rather comforting too. A finished world would be a smaller place. A world in which every question had already been closed and labelled would be strangely airless. But ours is not like that. Ours is a universe where the old familiar things can still lead to new mysteries, where a question about heat turns into a question about geometry, where the history of temperature becomes the history of what matter can be, where the beginning of the cosmos still asks more of us than we can presently deliver. There is humility in that, and relief as well. We are not standing at the end of inquiry, we are resting inside it. It is worth noticing how many of the deepest lessons in this journey involved limits. The highest temperature, the smallest meaningful scale, the shortest interval, where present theory begins to struggle. Limits in physics are sometimes misunderstood as disappointments, as if nature were simply telling us no. But the good limits are rarely like that. They are informative. They tell us what kind of world this is. The speed of light tells us that space and time are structured in a particular way. Absolute zero tells us something profound about thermal motion and order. The Planck temperature tells us that there is a point where the separate pillars of modern physics can no longer stand apart. A limit, properly understood, is not the end of thought. It is the place where thought has to become better. And yet, for all this seriousness, there remains a small smile in the whole affair. Because no matter how deep the topic becomes, there is still something delightfully human about asking it in the first place. How hot can anything get? It is exactly the sort of question our species would ask. Curious, impractical, slightly absurd, and completely sincere. It is what happens when a creature that once huddled around campfires eventually learns enough mathematics to wonder about the thermal frontier of the cosmos. One can imagine the whole arc of civilization in that contrast. Firelight to quantum gravity. A long way to go just to discover that the hottest possible thing may be the point where even our best explanations need help. If you think about it, that is almost funny. Not in a mocking way, but in the gentle way science often surprises us. We set out trying to measure heat, and end up asking whether space-time is fundamental. We build thermometers, and eventually find ourselves discussing the first instant of the universe. There is something deeply charming about that progression. It makes the human mind look both small and impressively stubborn. We are not built for Planck scales. We are built for berries and weather and social misunderstandings. And still, somehow, here we are, worrying away at the earliest thermal history of everything. Perhaps that is why topics like this make good company at the end of the day. They are large enough to quiet smaller noise. The mind that has been crowded with errands and messages and clocks and awkward conversations can sometimes loosen its grip when faced with the whole thermal architecture of reality. A worry about tomorrow morning has difficulty sounding quite so absolute, after a half hour spent considering whether the beginning of the universe required a quantum description of space-time. That does not solve daily life, unfortunately. Bills do not become optional just because the Planck regime is conceptually rich. But it can restore proportion, and proportion is sometimes one of the kindest things thought can offer before sleep. There is also something soothing in the direction of the story. We did not move toward greater and greater complication forever. In a sense, we moved backward toward a simpler but more extreme condition, where many later distinctions had not yet settled. Then we watched the universe cool into structure. The world became articulate by becoming less hot. That is a nice idea to carry into rest. The calm of evening is, in its own tiny way, part of the same logic. Activity gives way to stillness. Motion gives way to order. The mind cools down enough to let more stable patterns form. Sleep itself is not quite cosmology, though some nights it may feel as elusive as a theory of quantum gravity. But the metaphor is close enough to enjoy without abusing it. And so it is worth pausing right here, not to force a grand ending, but simply to notice where we have come. We began with warmth as a feeling. We ended with temperature as a frontier of theory. We walked through atoms and plasmas and stars in the young universe. We met Max Planck and saw why his name belongs to the natural scales of reality. We asked whether the hottest possible temperature was merely huge or something more significant, and found that it points directly toward the unfinished architecture of physics. We learned that the beginning of the cosmos may have lived near a regime where our present categories blur, and that nothing in the modern universe casually recreates those conditions. Most of all, we learned that what seems simple at the scale of daily life can become profound when followed carefully enough. That is, in a way, the whole spirit of this little journey. Science does not always drag us away from the familiar. Very often it returns us to the familiar with altered eyes. A mug of tea is still a mug of tea, but now it belongs to a thermal story that stretches all the way back to the early universe. A room is still a room, but now it is part of a cosmos that once burned with a heat beyond present theory. Your own body is still just your body, tired perhaps, comfortable perhaps, waiting for sleep perhaps, but it too is matter arranged from particles forged through a cooling history that began in unimaginable intensity. The ordinary survives, it simply becomes larger. Before we let this settle, I want to ask you one last gentle question. The same kind of question that seems to fit these quiet science evenings so well. Where are you listening from tonight, and what is the temperature like there in your little corner of the world? Is it cool enough for an extra blanket, warm enough to leave the window cracked, or somewhere in that very narrow band humans always seem to prefer while pretending to have stronger opinions than they really do? It is funny, after spending so much time thinking about the hottest temperature possible, how quickly the heart returns to such modest concerns. A room, a pillow, a breath of air, the exact right side of comfortable. If this long, slow wander through cosmic heat has helped you unwind, or given your thoughts something interesting and gentle to rest on, I would be very grateful if you liked the video and subscribed. It helps this quiet corner reach others who enjoy letting science do what it does best at the end of a day, which is not only inform, but steady the mind a little. There will always be more to ask, more limits to explore, more ordinary ideas hiding deeper layers underneath them, and there is something nice about meeting those questions one at a time without hurry. For now, though, there is no need to push further. The universe can keep its deepest furnace for the night. We have gone far enough to feel its glow without needing to stand inside it. We know that somewhere near the beginning of everything, reality may have passed through a temperature so extreme that our present theories still hesitate before it. We know that this limit is not just a number, but a sign that the fabric of the world has more to reveal. And we know that here, now, in this much cooler age of the cosmos, there is room for quiet, for sleep, and for the pleasant thought that even the calmest evening belongs to a universe with a far more dramatic past than it lets on. So settle in. Let the room be small again. Let the stars remain where they are. Let the oldest fire in the story fade back into the distance. You are here, in a late and gentle chapter of a cooling universe, and that is not a bad place to rest. Sleep well wherever you are, in whatever weather has found you tonight, under whatever temperature feels most kind.